Right now, as you sit wherever you are, perhaps in the gentle glow of your screen, maybe wrapped in the quiet comfort of night, something extraordinary is racing toward us through the darkness. Something that shouldn't exist. Yet here it is, defying every rule we thought we knew about our cosmic neighborhood. Welcome to the Sleepless How, where we explore the universe's most beautiful mysteries. I'm grateful you've chosen to spend this moment with me, wherever your curiosity has brought you tonight. If these cosmic stories spark wonder in your mind, I'd be honored if you'd consider leaving a like. It helps more dreamers find their way to these tales of the infinite. A gentle subscription means we can continue exploring together, one mystery at a time. Tonight, we venture into a story that is unfolding right now as we speak. In these very days of late 2025, astronomers around the world are tracking something unprecedented, something that's reaching the climax of its cosmic performance as it sweeps through the inner regions of our solar system. Their telescopes had caught sight of a visitor from the deep, not just from beyond our solar system, but from realms so distant that the very atoms composing this wanderer were forged in the furnaces of alien suns, billions of years before our own Earth had even begun to form. This visitor has a name that sounds almost mechanical, almost cold: Three-Eye Atlas. But don't let the clinical designation fool you. Behind those letters and numbers lies one of the most mysterious objects ever to grace our cosmic doorstep, carrying secrets that challenge everything we thought we understood about the universe beyond our solar system's edge. The three-eye tells us something profound. This is only the third interstellar visitor we've ever confirmed, the third wanderer from the spaces between stars that we've been fortunate enough to witness as it passed through our celestial home. Think about that for a moment. In all of human history, with all our watching and waiting and wondering about what lies beyond, we've only had three such opportunities to study matter that formed around alien suns. The first was One-Eye Oumuamua, that enigmatic cigar-shaped mystery that tumbled through our system in 2017, moving so strangely that some wondered if it might be artificial, a piece of alien technology rather than a natural object. It stretched our understanding, this elongated visitor that seemed to accelerate in ways that defied simple explanations. But it was small, dark, and by the time we truly realized what we were looking at, it was already speeding away into the cosmic dark, carrying its secrets with it. Then came Two-Eye Borisov in 2019, and this one seemed more familiar. A proper comet with a glowing coma and tail, behaving much as we'd expect a chunk of ice and rock to behave when heated by our sun. It was still extraordinary, still a visitor from another star system, but it followed the rules we thought we understood. It sublimated, it glowed, it developed a tail pointing away from the sun, just as comets should. But Three-Eye Atlas? This newcomer has decided to write its own rules entirely. Picture, if you will, the moment when astronomers first realized what they were seeing. The Atlas Survey System, a network of telescopes designed to scan the skies for potentially dangerous asteroids, captured this object as it approached from the outer reaches of our solar system. At first glance, it might have seemed routine. Space is full of rocks and ice after all. But as the orbital calculations began to take shape, as the mathematics revealed the true nature of this object's path through space, something extraordinary became clear. This wasn't following an elliptical orbit like the countless asteroids and comets that call our solar system home. Instead, its trajectory was hyperbolic, a cosmic highway that curved around our sun and then headed straight back out into the interstellar void. The numbers didn't lie. This object had come from somewhere else entirely, from the spaces between the stars, and it was just passing through our neighborhood on a journey that had likely lasted millions of years. But even as the excitement of discovery rippled through the astronomical community, something else became apparent. Something that would transform this from a simple case of another interstellar visitor into one of the most perplexing mysteries in modern astronomy. 3I Atlas wasn't behaving like a comet should behave. It wasn't following the cosmic script that billions of years of observation had taught us to expect. When the James Webb Space Telescope turned its unprecedented infrared gaze toward this visitor, what it found was so unusual that scientists had to double-check their instruments, run their calculations again, peer deeper into the data to make sure they weren't seeing things. The chemistry of 3I Atlas's glowing coma, that cloud of gas and dust that surrounds the solid nucleus, was dominated not by water vapor, as is typical for comets, but by carbon dioxide. Not just a little carbon dioxide mixed in with the expected water, but an overwhelming abundance of it, an 8-to-1 ratio of carbon dioxide to water, among the highest ever recorded in any comet anywhere. Imagine opening what you expect to be a bottle of water and finding it filled with something else entirely, something that challenges your basic assumptions about what should be inside. That's essentially what astronomers experienced when they analyzed the spectroscopic signature of 3I Atlas's coma. This discovery alone would have been enough to mark 3I Atlas as special, but the mysteries were only beginning to unfold. The visitor was already active, already producing its glowing coma and beginning to develop a tail at distances where most comets remain dormant and frozen. It had awakened from its cosmic slumber while still more than 6 times farther from the sun than Earth, in the cold depths where even the sun's warmth is barely a whisper. The TESS Space Telescope and the Swift Observatory caught these early signs of activity, detecting the telltale glow of hydroxyl radicals, fragments of water molecules torn apart by solar radiation. But the fact that this was happening so far out, in conditions where most cometary material should remain locked in ice, suggested that 3I Atlas was made of something different, something that responds to heat in ways we hadn't seen before. As astronomers began to piece together the puzzle of this visitor's journey, they realized they were looking at something far more ancient than anything in our solar system. Evidence pointed to an origin in the thick disk of our galaxy, that dense middle layer of the Milky Way where older stars reside. If their calculations were correct, 3I Atlas could be anywhere from 7 to 14 billion years old. To put that in perspective, our entire solar system, our Sun, Earth, all the planets we call neighbors, formed just 4.6 billion years ago. This visitor is a relic from when the universe was young, when the first generations of stars were still painting the cosmos with heavy elements. Think about the implications of that age, when 3I Atlas first coalesced in some distant stellar nursery. Our corner of the galaxy was empty space and drifting gas. The sun hadn't been born, Earth was not even a dream. This object has been wandering the galaxy since before our world existed, carrying within its icy heart the chemical signatures of stellar processes that occurred in the cosmic dawn. The trajectory itself tells a story of incredible speed and distance. 3I Atlas follows what astronomers call a hyperbolic orbit, not the gentle ellipse of objects bound to our sun, but a sharp curve that carries it in from the depths of interstellar space, around our star in a tight embrace, and then back out into the cosmic void. Its orbital eccentricity is so extreme that it makes previous interstellar visitors look almost leisurely by comparison. This speed, this trajectory, speaks to the vast scales of galactic motion. 3I Atlas didn't simply drift here on stellar winds. It has been moving with purpose and momentum for eons, possibly ejected from its birth system by gravitational encounters with massive objects, then shepherded across the light years by the subtle gravitational currents that flow between stars. But perhaps the most intriguing aspect of 3i Atlas isn't what it is, but what some have dared to suggest it might be. Astrophysicist Avi Loeb, known for his willingness to consider unconventional possibilities, has speculated whether this visitor could be something more than a natural comet. Could it be a probe, a piece of technology from another civilization, sailing between the stars on missions we can barely imagine? The scientific community has largely pushed back against such speculation, pointing to 3i Atlas's comet-like behavior, its coma, its tail, the way it responds to solar heating. These are the signatures of sublimating ice and dust, they argue, not the characteristics of artificial objects. Yet the unusual chemistry, the strange activity patterns, the remarkable structural integrity across billions of years, these factors keep the conversation alive in the margins of astronomical discourse. Whether natural wonder or something more exotic, 3i Atlas represents an unprecedented opportunity. As it makes its grand tour of our inner solar system over the coming months, it will offer telescopes around the world and in space a chance to study interstellar material up close. Each observation, each spectrum, each photograph adds another piece to the puzzle of what lies beyond our cosmic home. The visitor's schedule reads like a cosmic dance card. It swept past Mars in early October at a distance of just 0.19 astronomical units, closer than the planet's orbit around the Sun. Later this month, it will reach perihelion, its closest approach to our star, threading the needle between the orbits of Earth and Mars. In November, it will glide past Venus, and in December, it will make its closest approach to Earth at a distance of 1.8 astronomical units. Finally, in March of 2026, it will encounter Jupiter, that gravitational giant whose pull will give 3i Atlas one final acceleration as it departs our solar system forever. Each of these encounters offers a unique window into the visitor's nature. Ground-based telescopes are already capturing stunning images of its growing coma and developing tail. The Gemini South Observatory, the Hubble Space Telescope, and the James Webb Space Telescope are all turning their sophisticated eyes toward this cosmic traveler, each revealing new details about its composition and behavior. The public fascination has been extraordinary. Social media fills with images of this glowing visitor as it brightens in our skies. Amateur astronomers with backyard telescopes are contributing observations alongside professional observatories. There's something deeply moving about this. The idea that people around the world are looking up at the same cosmic visitor, sharing in the wonder of something that has journeyed across the galaxy to visit us. But beneath the visual spectacle lies a deeper mystery that keeps astronomers awake at night, working through the implications of what they're seeing. 3i Atlas challenges our understanding of how comets form, how they survive in interstellar space, and what the chemistry of distant star systems might look like. It's a library book from another solar system, written in a language we're still learning to read. The detective story is just beginning. Every observation raises new questions. Every measurement reveals new puzzles. Why hasn't this ancient wanderer broken apart during its long journey through space when so many comets fragment under much gentler stresses? What does its unusual chemistry tell us about the conditions where it formed? How many other such visitors might be passing through our solar system undetected, carrying their own secrets from the spaces between stars? As 3i Atlas continues its swift passage through our neighborhood, it carries with it the hopes and questions of an entire species suddenly confronted with tangible evidence of the wider galaxy. In its glowing tail, We see not just reflected sunlight, but the light of distant possibilities, the promise that we are not alone in space, that the universe is far stranger and more wonderful than we dared imagine. This cosmic visitor has broken the rules we thought governed the behavior of comets, challenged our assumptions about interstellar objects, and opened new chapters in the great book of astronomical knowledge. But its greatest gift may be the simplest, the reminder that mystery still exists in our universe, waiting to be discovered by anyone curious enough to look up at the night sky and wonder what lies beyond the familiar stars. The moment of discovery came not with fanfare or dramatic announcement, but in the quiet way that most revolutionary science begins, with a single data point that doesn't quite fit the pattern, noticed by someone paying careful attention to the endless stream of numbers flowing from our robotic sentinels in space. The Atlas survey system had been watching the sky with mechanical patience since its inception, its twin telescopes in Hawaii scanning for asteroids that might pose a threat to Earth. Night after night, these automated guardians captured thousands of images, processing them through algorithms designed to spot the telltale motion of objects moving against the star field. Most detections were routine, known asteroids following predictable paths, or newly discovered rocks that would soon be catalogued and forgotten. But in the early months of 2025, something appeared in the data that made the software pause, flag an anomaly, and send an alert to human astronomers for closer inspection. The object that would become known as 3I Atlas, first registered as little more than a moving dot of light, barely distinguishable from the cosmic background. But even in those earliest observations, there were hints that this was no ordinary visitor to our solar system. Its brightness varied in subtle ways, and more importantly, its motion across the sky didn't follow the gentle curves that characterize objects bound to our sun's gravitational embrace. Dr. Robert Werrick, the same astronomer who had first spotted the enigmatic Oumuamua years earlier, was among the first to examine the preliminary orbital calculations. What he saw in those numbers would have seemed impossible just a few decades ago, before we knew that the space between stars could deliver such gifts to our doorstep. The trajectory was hyperbolic. When the International Astronomical Union established the convention for designating interstellar objects, they chose the letter I to distinguish them from ordinary comets and asteroids. The number before the I indicates the order of discovery. 1I Oumuamua was first, 2I Borisov second, and now this newcomer would be designated 3I Atlas, acknowledging both its interstellar origin and the survey system that found it. There's something poetic about that designation. 3I, the third messenger from the spaces between stars, carrying information about stellar systems we may never visit, about processes we can only imagine. Each interstellar visitor is like a sample return mission that costs us nothing, delivering extraterrestrial material to our instruments free of charge. But as astronomers began their detailed observations of 3I Atlas, they discovered that this visitor had been trying to tell them something long before they'd noticed it was there. Archives of earlier observations captured by various sky surveys over the preceding months revealed that the object had been active, producing a detectable coma of gas and dust, while still incredibly far from the Sun. The Transiting Exoplanet Survey Satellite, or TESS, had been monitoring a patch of sky that happened to include 3I Atlas in its field of view. When astronomers went back through the data, they found evidence of the comet's activity dating back to when it was still more than 6 astronomical units from the Sun, 6 times farther than Earth's orbit. At such distances, the solar heating should be far too weak to sublimate the ice that typically creates a comet's glowing atmosphere. Swift, The space-based observatory, originally designed to study gamma-ray bursts, had also captured signatures of 3I Atlas's early awakening. Its sensitive instruments detected the spectral lines of hydroxyl radicals, molecular fragments produced when water molecules are broken apart by solar radiation. But finding these signatures at such vast distances from the Sun raised immediate questions about what kind of ice was sublimating and why it was responding to such weak heating. Dr. Davide Farnocchia at NASA's Jet Propulsion Laboratory worked with his team to refine the orbital calculations, using observations spanning several months to nail down the precise path 3I Atlas was following through space. The numbers they arrived at painted a picture of incredible speed and cosmic scale. This object was moving at more than 40 kilometers per second relative to the Sun, fast enough to cross the diameter of Earth in just over 5 minutes. More remarkably, when they traced this trajectory backward through time, the calculations suggested that 3I Atlas had been traveling through interstellar space for millions, perhaps billions of years before its encounter with our solar system. Its path didn't point back to any nearby star system, suggesting it had either travelled an enormous distance or had its trajectory altered by gravitational encounters with other massive objects during its journey through the galaxy. The orbital mechanics revealed something else extraordinary: the extreme nature of 3I Atlas's trajectory. Its orbital eccentricity, a measure of how stretched or circular an orbit is, registered at approximately 3.5. To put that in perspective, a perfect circle has an eccentricity of 0, while Earth's nearly circular orbit has an eccentricity of just 0.017. Even the highly elongated orbits of long-period comets rarely exceed an eccentricity of 1. But 3I Atlas was following a path so hyperbolic, so extreme, that it made even Oumuamua's eccentric orbit look tame by comparison. This extreme trajectory spoke to the violence of 3I Atlas's ejection from its birth system. Something catastrophic had occurred in its distant past, perhaps a close encounter with a massive planet, or the death throes of its parent star that had flung this object into the interstellar void at tremendous speed. For billions of years it had wandered the galaxy, a cosmic exile carrying the chemical fingerprints of its origin. The early activity detected by Tess and Swift became even more intriguing when compared to the behavior of typical comets. Most comets remain dormant until they approach within about 3 astronomical units of the Sun, roughly the distance of the asteroid belt. Only then does solar heating become strong enough to sublimate their ices and create the characteristic coma and tail. But 3I Atlas had awakened much farther out, suggesting that either its composition was dramatically different from typical comets, or it contained materials that were far more volatile than the water ice that dominates most comet nuclei. Some researchers began to speculate about exotic ices, perhaps carbon monoxide or carbon dioxide frozen at the low temperatures of interstellar space, that might sublimate at much greater distances from the Sun. Others wondered if 3I Atlas might contain radioactive elements that provided internal heating, or if its surface properties somehow concentrated the weak solar energy available at such vast distances. The mystery deepened when spectroscopic observations revealed the unusual chemistry of the comet's coma. Rather than the water-dominated atmosphere typical of most comets, 3I Atlas showed an overwhelming abundance of carbon dioxide. This wasn't just unexpected, it was unprecedented. Never before had astronomers observed a comet with such an extreme chemical composition, where carbon dioxide so dramatically outweighed water vapor. Dr. Stefano Bagnulo of the Armagh Observatory led a team using the Very Large Telescope in Chile to study the polarization of light from 3I Atlas's coma. Their observations suggested that the dust grains surrounding the nucleus had properties unlike those seen in solar system comets, possibly indicating a different formation environment or chemical composition. Each new observation raised more questions than it answered. The comet's nucleus appeared to be remarkably intact, despite its obvious age and the harsh environment of interstellar space. Unlike many comets that fragment when subjected to thermal stress, 3I Atlas showed no signs of breaking apart, even as it approached the Sun and its activity increased. The implications were staggering. If 3I Atlas truly represented material from another star system, it offered an unprecedented opportunity to study the chemistry and physics of planetary formation beyond our solar neighborhood. Every spectrum, every image, every measurement was potentially revealing secrets about how planets and comets form around other stars, about the diversity of chemical processes occurring throughout the galaxy. The true revelation came when humanity's most sophisticated eye turned toward this cosmic wanderer, bringing into focus details that would rewrite our understanding of what interstellar visitors could be. The James Webb Space Telescope, that marvel of engineering floating in the darkness beyond Earth's orbit, had been designed to peer into the deepest reaches of space and time. Its mirror, nearly 3 times larger than Hubble's, could capture infrared light with unprecedented sensitivity. When JWST trained its golden gaze on 3I Atlas, the spectrum it revealed was so extraordinary that astronomers initially questioned whether their instruments were functioning correctly. The data that flowed back to Earth painted a picture that defied every expectation built from decades of comet observation. Where scientists expected to find the familiar signature of water vapor, the dominant component of virtually every comet coma ever studied, they instead discovered something that seemed almost impossible. The spectroscopic analysis revealed an overwhelming abundance of carbon dioxide, outnumbering water molecules by a ratio of 8 to 1. 8 to 1. Let that sink in for a moment. In the world of comet chemistry, this was like finding a desert in the middle of an ocean. Water ice is the fundamental building block of comet nuclei, the material that creates the glowing atmosphere we associate with these visitors from the outer solar system. To find a comet where carbon dioxide so dramatically dominates water is to discover something that challenges our basic understanding of how these objects form and evolve. Dr. Geronimo Villanueva, a planetary scientist at NASA's Goddard Space Flight Center, led the team analyzing JWST's spectroscopic observations. When he first saw the data streaming from the telescope, he ran the analysis multiple times, checking for instrumental errors or contamination that might explain such an unusual result. But the signature was unmistakable. 3I Atlas was releasing carbon dioxide at a rate that dwarfed its water production, creating a coma composition unlike anything in the astronomical literature. To understand how remarkable this discovery truly is, consider what we know about typical comets. When Halley's Comet last visited our inner solar system, detailed analysis revealed a coma that was roughly 80% water vapor by volume. The rest consisted of carbon monoxide, carbon dioxide, methane, ammonia, and various other molecules. But water dominated the mixture so completely that comets are often described as dirty snowballs, chunks of ice mixed with rocky material. This water-dominated chemistry reflects the conditions where most comets formed, in the cold outer regions of our solar system where water ice could condense and accumulate. The giant planets, Jupiter, Saturn, Uranus, and Neptune, created gravitational boundaries that determined which materials could condense at different distances from the Sun. Beyond what astronomers call the snow line, roughly 3 astronomical units from the Sun, temperatures were low enough for water to freeze, creating the icy building blocks from which comets would eventually coalesce. But 3I Atlas tells a different story entirely. Its extreme carbon dioxide abundance suggests formation conditions that were far colder than anything in our solar system, temperatures where carbon dioxide itself could freeze into solid ice. In our corner of the galaxy, carbon dioxide sublimates, transitions directly from solid to gas at temperatures around -78 degrees Celsius. For carbon dioxide ice to remain stable and accumulate in significant quantities, temperatures would need to be far below this threshold, in the realm of -200 degrees Celsius or colder. Such extreme cold exists in the depths of interstellar space, in the dark molecular clouds where new stars are born, or in the outer reaches of stellar systems where the warmth of a parent star barely registers above the cosmic background temperature. The chemistry of 3I Atlas suggests it formed in such an environment where carbon dioxide could freeze and remain stable for billions of years. The implications cascade through our understanding of planetary formation like ripples in a cosmic pond. If 3I Atlas formed in such extreme conditions, it offers a window into stellar systems very different from our own, perhaps systems with different chemical abundances, different temperature profiles, or different evolutionary histories. The carbon dioxide abundance might reflect the metallicity of its birth environment, the availability of carbon and oxygen relative to other elements, or even the influence of nearby stellar processes that altered the local chemistry. Dr. Martin Cordiner, an astrochemist at NASA, worked with international colleagues to model the formation conditions that could produce such an extreme carbon dioxide to water ratio. Their calculations, published in preprint form on the Archive server, suggested that 3I Atlas might have formed in a region where carbon was significantly more abundant than in our solar system's formative disk. This could occur in stellar systems with different evolutionary histories where previous generations of stars had enriched the local environment with carbon-rich material. The archive papers that documented these findings read like dispatches from an alien world. Teams from observatories around the globe contributed spectroscopic data, each confirming the extraordinary nature of 3I Atlas's composition. The European Space Agency's ground-based observatories added their observations, while teams using the Atacama Large Millimeter Array captured the molecular signatures in exquisite detail. But the carbon dioxide abundance was only part of the story. The relative absence of water vapor suggested that 3I Atlas had experienced a formation environment where water ice was either unavailable or unstable. This might occur in stellar systems with different snowline locations, where the habitable zone and ice formation regions were positioned differently than in our solar system. Or it might reflect formation in the interstellar medium itself, where molecular clouds with unusual chemistry could produce icy bodies with compositions radically different from anything we've seen before. The discovery also raised profound questions about the survival of such exotic chemistry over cosmic time. Carbon dioxide ice is more volatile than water ice, sublimating at higher temperatures. For 3I Atlas to retain such an abundance of carbon dioxide after potentially billions of years in space suggests either that its nucleus is far larger than initially estimated, providing the mass necessary to gravitationally retain its atmosphere, or that it has spent most of its existence in the extreme cold of interstellar space, where even carbon dioxide remains locked in solid form. Dr. Sylvia Protopapa at the Southwest Research Institute led modeling efforts to understand how such composition might affect the comet's behavior as it approached the Sun. Their simulations suggested that the high carbon dioxide content could explain 3I Atlas's early activity, detected when it was still more than 6 astronomical units from the Sun. Unlike water ice, which requires substantial solar heating to sublimate, carbon dioxide ice can begin outgassing at much lower temperatures, creating the early coma observed by Tess and Swift. The modeling also revealed implications for the comet's structural evolution. As carbon dioxide sublimates more readily than water, the outer layers of 3I Atlas's nucleus might be undergoing rapid changes, creating a complex surface topography as different materials respond to solar heating at different rates. This could explain some of the unusual light curves observed by ground-based telescopes, where the comet's brightness varied in ways that didn't match simple models of rotating nuclei. The chemical analysis extended beyond just carbon dioxide and water. JWST's spectrographs detected trace amounts of carbon monoxide, methane, and even more exotic molecules that provided additional clues about formation conditions. The relative abundances of these species painted a picture of chemistry that had been frozen in time, preserved in the deep cold of interstellar space for eons before 3I Atlas began its journey toward our Sun. Perhaps most intriguingly, the isotopic ratios detected in 3I Atlas's coma differed subtly from those found in solar system objects. These isotopic fingerprints are like DNA for astronomical objects, reflecting the nuclear processes that created the elements composing them. The slight differences suggested that 3I Atlas had formed in a stellar environment with a different history of supernova enrichment, stellar nucleosynthesis, or chemical evolution than our own solar system. The scientific papers documenting these discoveries accumulated on Archive throughout 2025, each adding new pieces to the puzzle of 3I Atlas's origin and composition. Teams from institutions around the world contributed observations, theoretical models, and comparative analyses that built a comprehensive picture of this extraordinary visitor. The collaboration spanned continents and disciplines, bringing together experts in comet science, astrochemistry, stellar evolution, and galactic astronomy to decode the messages hidden in the spectrum of this ancient wanderer. These findings forced a fundamental reconsideration of what we thought we knew about comet formation and evolution. If interstellar space could preserve such exotic chemistry for billions of years, and if stellar systems throughout the galaxy were producing icy bodies with compositions so different from our own, then the universe was far more chemically diverse than we had dared imagine. The diversity revealed in 3I Atlas's chemistry was matched only by the breathtaking velocity at which it carried these ancient signatures through our solar system, moving like a stone skipping across the surface of space-time itself. When astronomers calculated the precise orbital mechanics of 3I Atlas, they discovered they were tracking something that redefined their understanding of interstellar motion. The comet was racing through space at more than 44 kilometers per second relative to our Sun, a velocity so extreme that it could cross the entire diameter of Earth in less than 5 minutes. To put this in perspective, this speed is roughly 160,000 kilometers per hour, fast enough to travel from New York to Los Angeles in barely 2 minutes. But raw velocity tells only part of the story. The true measure of 3I Atlas's extraordinary nature lies in its orbital eccentricity, a mathematical description of just how dramatically its path deviates from a perfect circle. Dr. Davide Farnocchia's team at NASA's Jet Propulsion Laboratory calculated an eccentricity of approximately 3.5 for 3I Atlas. A number that would have seemed impossible just decades ago when our understanding of solar system dynamics was limited to the gentle ellipses of planets and the elongated but still bound orbits of periodic comets. To understand the significance of this number, imagine the difference between a leisurely stroll through a park and a bullet fired from a rifle. Earth's nearly circular orbit around the Sun has an eccentricity of just 0.017, so close to zero that our planet's path is almost a perfect circle. Even the highly elongated orbits of long-period comets, stretched by gravitational encounters with the giant planets, rarely exceed an eccentricity of 1.0, the mathematical boundary between bound and unbound motion. But 3i Atlas soars far beyond this threshold, following what mathematicians call a hyperbolic trajectory. This isn't merely a fast orbit. It's not an orbit at all in the conventional sense. Instead, it's a cosmic flyby, a graceful curve that brings the comet close enough to feel our sun's gravitational embrace before carrying it inexorably back into the interstellar void. The physics underlying this trajectory speak to fundamental principles that govern motion throughout the universe. Every object in the cosmos must balance two competing forces: the gravitational pull that seeks to bind it to massive bodies, and its own kinetic energy that drives it forward through space. When kinetic energy wins decisively, as it has with 3i Atlas, the result is a hyperbolic escape, a one-way ticket away from gravitational captivity. This victory of motion over gravity required an initial velocity that exceeded what astronomers call the escape velocity from our solar system. At the distance where 3i Atlas first entered the Sun's sphere of influence, roughly 1,000 astronomical units away, the escape velocity is relatively modest, just a few kilometers per second. But 3i Atlas arrived with kinetic energy far exceeding this threshold, carrying momentum accumulated over millions or billions of years of interstellar travel. The comparison to previous interstellar visitors reveals just how exceptional 3i Atlas truly is. When 1i Oumuamua swept through our solar system in 2017, it moved at roughly 26 kilometers per second relative to the Sun, fast enough to earn its status as an interstellar visitor, but sedate compared to 3i Atlas's breakneck pace. 2i Borisov, the comet-like visitor that followed in 2019, traveled at about 32 kilometers per second, still significantly slower than our current guest. These velocity differences aren't merely academic curiosities, they're clues to the cosmic histories of these objects. The faster an interstellar visitor moves, the more violent its ejection from its birth system must have been, or the longer it has been accelerated by gravitational encounters during its journey through the galaxy. 3i Atlas's extreme speed suggests a particularly dramatic origin story, perhaps ejection by a close encounter with a massive planet, or even a stellar companion. The trajectory calculations reveal another remarkable aspect of 3i Atlas's journey. When astronomers trace its path backward through time, accounting for the gravitational influences of nearby stars, they find no obvious point of origin. Unlike some previous interstellar visitors whose paths could be traced back to specific stellar systems, 3i Atlas appears to have wandered the galaxy for so long that its birth system has become lost in the cosmic shuffle. This extended journey speaks to distances that challenge human comprehension. Conservative estimates suggest 3i Atlas has traveled at least several hundred light-years to reach us, covering a distance so vast that light itself, the fastest thing in the universe, would take centuries to traverse it. More aggressive calculations, based on the comet's apparent age and the random motions of stars in our galactic neighborhood, suggest it might have journeyed thousands of light years, wandering from one side of our spiral arm to the other during its eons-long odyssey. The galactic environment through which 3i Atlas has traveled is not empty space, but a dynamic realm filled with gravitational currents, magnetic fields, and tenuous clouds of gas and dust. Over millions of years, these influences can subtly alter an object's trajectory, deflecting it from its original path and accelerating or decelerating its motion through complex gravitational interactions. Dr. Fabo Feng at the Carnegie Institution for Science led efforts to model 3I Atlas's possible trajectory through the galaxy using sophisticated computer simulations that account for the gravitational influences of thousands of nearby stars. His team's calculations suggested that the comet's current velocity could be the result of multiple gravitational assists from stellar encounters over cosmic time, each interaction adding energy to its motion and accelerating it toward our solar system. These models reveal the galaxy as a vast gravitational pinball machine, where objects like 3I Atlas bounce between stellar influences, gaining and losing energy in complex ways that can produce exactly the kind of high-velocity trajectories we observe. The comet's speed becomes a fossil record of its cosmic journey, encoding information about every significant gravitational encounter it has experienced during its travels through interstellar space. The mathematical elegance of 3I Atlas's trajectory belies the violent history it represents. To achieve such extreme velocity, something catastrophic must have occurred in the comet's distant past. Perhaps the death of its parent star, the gravitational disruption of its birth system by a passing stellar companion, or a close encounter with a massive planet that flung it into the interstellar void with tremendous force. Theoretical models suggest several scenarios that could produce such high-velocity ejection. A supernova explosion in the comet's birth system could accelerate nearby objects to tremendous speeds, launching them into interstellar space as high-velocity refugees from stellar catastrophe. Alternatively, the gravitational influence of a massive planet, perhaps a hot Jupiter migrating inward toward its star, could scatter smaller objects throughout the system, flinging some into hyperbolic escape trajectories. The comet's velocity also influences how it interacts with our solar system during its brief visit. Unlike bound objects that spend months or years in our neighborhood, 3I Atlas races through on a compressed timeline, its high speed limiting the time available for detailed study. The same velocity that makes 3I Atlas extraordinary also makes it challenging to observe, as it streaks across the sky faster than many telescopes can easily track. Current observations suggest that 3I Atlas will reach its maximum velocity relative to the Sun as it passes through perihelion, the closest point of its trajectory. There, accelerated by the Sun's gravitational pull like a cosmic slingshot, it will achieve speeds approaching 50 kilometers per second before beginning its long deceleration back into interstellar space. This gravitational acceleration demonstrates one of the most beautiful principles in orbital mechanics: the conservation of energy. As 3I Atlas approaches the Sun, its gravitational potential energy converts to kinetic energy, accelerating the comet to even greater speeds. Then, as it recedes, this process reverses, with kinetic energy converting back to potential energy as the Sun's gravity tries in vain to slow the comet's escape. The precise measurements of 3I Atlas's velocity and trajectory have already contributed to our understanding of stellar kinematics, the study of how stars and other objects move through the galaxy. By analyzing the motion of interstellar visitors like 3I Atlas, astronomers can infer properties of the galactic gravitational field, the distribution of dark matter, and the dynamics of stellar populations. The comet's trajectory also provides a natural laboratory for testing our understanding of solar system dynamics on extreme scales. As 3I Atlas passes close to our planets, its path will be subtly deflected by their gravitational influences, providing precise measurements of planetary masses and testing the accuracy of our models of multi-body gravitational interactions. These precise gravitational measurements do more than test our theories of celestial mechanics. They also provide crucial clues about where 3I Atlas originated, revealing a story that stretches back to the very dawn of our galaxy's evolution. When astronomers analyze the trajectory and velocity of interstellar visitors, They're essentially working backward through time, using the laws of physics to unravel the cosmic history encoded in motion. For 3i Atlas, this detective work has led to a remarkable conclusion. This ancient wanderer likely originated not from the thin disk where our sun resides, but from the thick disk of the Milky Way, a stellar population so old that it formed when the universe itself was still in its youth. The evidence comes from several converging lines of investigation. The comet's high velocity relative to the local standard of rest, its steep inclination relative to the galactic plane, and its unusual chemical composition all point toward an origin in the galaxy's thick disk population. This stellar realm, which surrounds our galaxy's central bulge like a puffy cushion, contains some of the Milky Way's oldest residents, stars that formed between 7 and 14 billion years ago, when the cosmos was less than half its current age. To appreciate the profound implications of this age estimate, consider that our entire solar system, the Sun, Earth, all the planets we call neighbors, and every living thing we know, formed just 4.6 billion years ago from a disk of gas and dust enriched by previous generations of stars. When 3i Atlas first coalesced in some distant stellar nursery, our corner of the galaxy was nothing more than diffuse hydrogen and helium, still waiting for the gravitational collapse that would eventually birth our sun. This makes 3i Atlas quite literally a message in a bottle from the galaxy's youth, carrying within its ancient nucleus the chemical fingerprints of stellar processes that occurred during what astronomers call cosmic noon, that extraordinary epoch between 8 and 12 billion years ago when star formation throughout the universe reached its peak intensity. Picture the Milky Way as it existed during cosmic noon, and you would see a galaxy very different from the one we inhabit today. Star formation was proceeding at a rate perhaps 10 times higher than we observe now, with massive stellar nurseries blazing throughout the galactic disk. The night sky would have been dramatically brighter, painted with the fierce light of young, hot stars that burned through their nuclear fuel in just millions of years before exploding as supernovae, enriching the interstellar medium with heavy elements forged in their cores. The thick disk region where 3i Atlas likely formed was a particularly active stellar maternity ward during this epoch. Unlike the relatively ordered thin disk where our sun resides, where stars move in neat circular orbits around the galactic center, the thick disk is a more chaotic environment, populated by stars with highly elliptical orbits and random inclinations. This kinematic signature reflects the violent conditions present during the galaxy's youth, when mergers with smaller galaxies and gravitational interactions stirred the stellar population into complex motions. Dr. Tommaso Marchetti at the European Space Agency led research that analyzed the galactic population to which 3i Atlas most likely belongs. Using data from the Gaia Space Telescope, which has precisely measured the motions of more than 1 billion stars in our galaxy, his team compared the comet's velocity vector to the known kinematics of different stellar populations. The match with thick disk objects was striking. 3i Atlas moves through space with exactly the kind of high velocity and steep galactic orbit characteristic of this ancient stellar family. The chemical composition revealed by JWST's spectroscopic observations provides additional evidence for this ancient origin. The extreme carbon dioxide abundance and unusual isotopic ratios detected in 3i Atlas's coma are consistent with formation in a stellar environment with different metallicity than our solar system, exactly what we would expect from an object that formed when the galaxy was chemically younger, before billions of years of stellar nucleosynthesis had enriched the interstellar medium with the heavy elements we see today. During cosmic noon, the typical molecular cloud from which stars and planetary systems formed contained a lower abundance of elements heavier than hydrogen and helium. This low metallicity environment would favor the formation of icy bodies with compositions rich in simple molecules like carbon dioxide and carbon monoxide, rather than the water-dominated chemistry we see in comets formed in more recent epochs. The exotic chemistry of 3I Atlas may thus be a direct reflection of the galactic conditions that existed billions of years before our solar system was born. The journey that brought 3I Atlas from its birth system to our solar system spans not just incredible distances, but vast epochs of cosmic time. Over the course of 7 to 14 billion years, this ancient wanderer has witnessed the evolution of our galaxy from its chaotic youth into the more settled spiral structure we see today. It has travelled through stellar associations that have long since dispersed, past stars that have exhausted their nuclear fuel and died, through regions of space that have been repeatedly enriched by supernova explosions and stellar winds. The galactic environment through which 3I Atlas has journeyed has itself evolved dramatically during the comet's lifetime. When it first began its wandering, the Milky Way was still actively accreting smaller satellite galaxies, events that would have stirred the stellar disk and created gravitational perturbations capable of scattering objects like comets into high-velocity trajectories. The galaxy's spiral arms, those magnificent structures that organize star formation today, were less well-defined during cosmic noon, creating a more turbulent environment for interstellar travel. Computational models of galactic evolution suggest that objects like 3I Atlas could have been scattered from their birth systems by a variety of mechanisms. Close encounters between stars in the dense stellar clusters common during cosmic noon could have disrupted planetary systems, flinging comets into interstellar space. Alternatively, the passage of molecular clouds through stellar systems could have gravitationally perturbed the outer regions where comets typically reside, sending some on escape trajectories. The survival of 3I Atlas over such vast timescales is itself remarkable. During its billion-year journey through interstellar space, it would have been exposed to cosmic rays, ultraviolet radiation from distant stars, and occasional collisions with interstellar dust grains. The fact that it has retained enough volatile material to produce an observable coma when heated by our Sun suggests either that it began as a much larger object and has gradually sublimated away its outer layers, or that it has spent most of its journey in the cold depths between stars, where even the most volatile ices remain frozen. Recent theoretical work by Dr. Amaya Moro-Martin at the Space Telescope Science Institute has explored the population dynamics of interstellar objects like 3I Atlas. Her models suggest that for every interstellar visitor we detect, millions more pass through our solar system unobserved, too small or too dark to register on our instruments. This implies that space is filled with ancient wanderers like 3I Atlas, carrying chemical and isotopic records of stellar processes that occurred throughout cosmic history. The thick disk origin of 3I Atlas also provides insights into the early evolution of planetary systems throughout the galaxy. If objects like this comet were common in the galactic environment billions of years ago, they might have played important roles in delivering water and organic compounds to newly formed planets. The high carbon dioxide content of 3I Atlas suggests that the building blocks of atmospheres, and potentially life itself, might have had very different compositions in the galaxy's youth than we observe in our solar system today. The isotopic ratios preserved in 3I Atlas's nucleus represent a form of cosmic archaeology, encoding information about the stellar nucleosynthesis processes that were active during cosmic noon. Different generations of stars produce heavy elements in different proportions, and these signatures become incorporated into the icy bodies that form in their circumstellar disks. By analyzing the isotopic composition of interstellar visitors like 3I Atlas, astronomers can reconstruct the history of chemical enrichment in our galaxy. The comet's ancient age also raises intriguing questions about the conditions that existed in planetary systems throughout the galaxy's early history. During cosmic noon, when star formation was at its peak, the typical spacing between stellar systems would have been much smaller than it is today. This could have facilitated the exchange of material between different planetary systems, with objects like 3I Atlas serving as carriers of chemical information across interstellar distances. The dynamical environment of the thick disk, with its population of stars on highly elliptical and inclined orbits, would have created frequent close encounters between stellar systems. These interactions could have scattered planetary material across vast distances, seeding the galaxy with a population of interstellar wanderers that preserve samples from countless different stellar environments. The possibility that ancient civilizations might have seeded the galaxy with wandering messengers adds an entirely different dimension to our interpretation of objects like 3I Atlas, transforming what might be a purely geological story into something far more provocative. In the scientific community, few researchers have been as willing to explore unconventional possibilities as Dr. Avi Loeb of Harvard University. When 3I Atlas first revealed its unusual characteristics, Loeb did what he has become known for throughout his career. He asked the question that others were perhaps thinking but hesitant to voice. Could this ancient wanderer be something more than a natural comet? Could it be a piece of technology, an artifact from a civilization that mastered interstellar travel long before our species even existed? Loeb's speculation wasn't born from wild imagination, but from a careful consideration of the anomalies that made 3I Atlas so difficult to explain through conventional comet science. The extreme carbon dioxide abundance, the early activity at vast distances from the Sun, the structural integrity across billions of years, the unusual trajectory that seemed to defy simple gravitational explanations. Each of these characteristics, while individually explicable through exotic natural processes, collectively painted a picture that challenged traditional understanding. The artificial hypothesis, as Loeb presented it, wasn't claiming that 3I Atlas was definitely a spacecraft or probe. Instead, he was arguing for what philosophers of science call inference to the best explanation. When faced with multiple possible interpretations of unusual data, we should consider all reasonable possibilities, including those that might seem unconventional. If a natural explanation requires invoking extremely rare conditions, unusual chemistry, and multiple coincidences, then perhaps we should also consider whether an artificial origin might provide a simpler, more elegant explanation. The characteristics that caught Loeb's attention were indeed remarkable when viewed through the lens of potential technology. The comet's ability to remain structurally intact across billions of years while continuously losing material through sublimation suggested either an enormous initial mass or some mechanism for maintaining structural coherence that natural comets typically lack. Its early activity, beginning at distances where solar heating should be negligible, could indicate internal energy sources rather than simple solar-driven sublimation. Most intriguingly, the extreme hyperbolic trajectory of 3I Atlas could be interpreted as evidence of propulsion rather than purely gravitational motion. While the mathematics of the orbit were consistent with a natural flyby, the specific velocity and path could also be explained by a controlled trajectory designed to survey multiple planetary systems during a single passage through the galaxy. The broader scientific community responded to Loeb's speculation with the kind of measured skepticism that defines good science. Dr. Alan Fitzsimmons at Queen's University Belfast led a consortium of observers who pointed to the clear signatures of sublimating ice in 3I Atlas's spectrum, evidence that strongly supported a natural comet interpretation. The detection of hydroxyl radicals, carbon dioxide and dust particles in the coma were exactly what one would expect from heated ice, not from any known form of artificial technology. Dr. Robert Verick, who had discovered the object, emphasized that while 3I Atlas was certainly unusual, all of its observed characteristics could be explained by natural processes, albeit exotic ones. The extreme carbon dioxide abundance, while unprecedented, wasn't impossible for a comet formed in unusual conditions. The early activity could result from highly volatile ices that sublimate at lower temperatures than typical cometary materials. The debate that ensued revealed something profound about the nature of scientific inquiry itself. Science advances through a delicate balance between healthy skepticism and openness to new possibilities. Too much skepticism and revolutionary discoveries might be dismissed before they're properly investigated. Too much openness and scientific rigor gives way to unfounded speculation. The controversy surrounding 3I Atlas illustrated this tension perfectly. Dr. Michelle Bannister at the University of Canterbury provided perhaps the most nuanced perspective on the debate. She acknowledged that while the artificial hypothesis was intriguing, the burden of proof for such an extraordinary claim would require extraordinary evidence. The presence of organic compounds, the response to solar heating, and the spectroscopic signatures all strongly favored a natural interpretation. However, she also emphasized that the unusual nature of 3I Atlas highlighted how much we still didn't understand about comet formation and evolution. The controversy also reflected broader tensions within the search for extraterrestrial intelligence. Traditional SETI efforts focus on detecting radio signals or other electromagnetic communications from distant civilizations. But as our understanding of interstellar travel has evolved, some researchers have begun considering whether advanced civilizations might prefer to send physical artifacts rather than radio messages across interstellar distances. The concept isn't entirely far-fetched when viewed from the perspective of information theory. A physical probe, even a simple one, could carry far more information than any electromagnetic signal of equivalent energy cost. Such a probe could conduct detailed surveys of planetary systems, collect samples, and even reproduce itself using local materials, capabilities that no radio transmission could match. Dr. Jacob Haq Misra at the Blue Marble Space Institute of Science has written extensively about the possibility that interstellar space might already contain a network of ancient probes launched by civilizations that arose and perhaps fell billions of years ago. These hypothetical artifacts, sometimes called Bracewell probes, after the scientist who first proposed the concept, could be so old and so numerous that encountering them might be more likely than receiving contemporary radio signals from active civilizations. The theoretical framework for such probes suggests they would need to be almost indistinguishable from natural objects to survive the harsh environment of interstellar space for billions of years. Cosmic radiation, micrometeorite impacts, and the gradual decay of any artificial materials would gradually erode obvious signs of technology. What remained after cosmic ages might appear natural to cursory observation, revealing its artificial nature only through subtle anomalies in behavior or composition. This perspective transforms our interpretation of objects like 3I Atlas. Instead of asking whether they show obvious signs of technology, we might ask whether they show subtle deviations from expected natural behavior, exactly the kinds of anomalies that make 3I Atlas so puzzling to conventional comet science. The philosophical implications of this debate extend far beyond the specific case of 3I Atlas. How do we distinguish between exotic natural phenomena and ancient artificial artifacts? What level of evidence would be sufficient to conclude that an interstellar visitor might be technological in origin? These questions touch on fundamental issues in the philosophy of science, particularly the problem of distinguishing between different types of explanations for the same observations. Carl Sagan's famous dictum that extraordinary claims require extraordinary evidence provides one framework for approaching such questions. From this perspective, the artificial hypothesis for 3I Atlas would require evidence that couldn't possibly be explained by natural processes, perhaps the detection of artificial isotopes, clearly manufactured materials, or unambiguous signs of information storage or processing capability. However, critics of this approach argue that it might be inherently biased against recognizing truly ancient artifacts. After billions of years in space, any artificial materials would have been weathered and altered beyond easy recognition. The very age that would make such artifacts so scientifically valuable would also make them most difficult to distinguish from natural objects. The debate has also highlighted the importance of international cooperation in studying unusual objects like 3I Atlas. No single observation or instrument can definitively resolve questions about the object's nature. Instead, the scientific community must pool observations from multiple telescopes across different wavelengths, using various analytical techniques to build a comprehensive picture of what we're seeing. The European Space Agency's contribution to these observations has been particularly valuable, with ground-based observatories across Europe providing complementary data to space-based observations. This international effort reflects the global nature of modern astronomy, where major discoveries require coordination across multiple institutions and countries. The controversy has also influenced how astronomers approach the study of other unusual interstellar visitors. The detection methods, analysis techniques, and theoretical frameworks developed for 3I Atlas are now being applied to other anomalous objects, creating a more systematic approach to identifying and characterizing interstellar visitors that don't fit conventional categories. Perhaps most importantly, the debate has encouraged a more nuanced understanding of what constitutes scientific evidence. Rather than simply accepting or rejecting the artificial hypothesis, the scientific community has used it as motivation to conduct more thorough observations and develop more sophisticated models of natural comet behavior. This process has advanced our understanding regardless of whether 3I Atlas proves to be natural or artificial. The rigorous observational campaigns inspired by this controversy revealed something even more remarkable than the debate itself, evidence that 3I Atlas had been active long before anyone realized it was there, awakening from its cosmic slumber in the cold depths where conventional comet science says activity should be impossible. The discovery came through the kind of careful archival detective work that exemplifies modern astronomy at its best. When the Transiting Exoplanet Survey satellite, known as TESS, had been monitoring distant stars for the subtle dimming that might indicate orbiting planets, its wide-field cameras had inadvertently captured something far closer to home. Deep in the archived data from early 2025, astronomers found the telltale signature of 3I Atlas already glowing with a detectable coma when it was still more than 6.4 astronomical units from the Sun. To appreciate how extraordinary this discovery was, Consider that 6.4 astronomical units places the comet beyond the orbit of Jupiter, in the cold outer reaches of our solar system, where sunlight arrives as little more than a distant whisper. At such distances, the solar energy reaching each square meter of surface is less than 3% of what Earth receives. For comparison, this is roughly equivalent to the illumination you might experience from a 60-watt bulb viewed from across a large auditorium. Dr. Tony Farnham at the University of Maryland led the team that analyzed these archived TESS observations. When he first spotted the faint glow surrounding 3I Atlas in images captured months before its official discovery, his initial reaction was to double-check the data processing. Comets simply don't behave this way. The standard model of comet activity, built from decades of observations of solar system comets, predicts that significant coma development should begin only when these icy visitors approach within roughly 3 astronomical units of the Sun, the approximate distance of the asteroid belt. The physics behind this prediction are straightforward and well established. Comet nuclei are primarily composed of water ice mixed with rocky material and more exotic ices like carbon monoxide and carbon dioxide. When solar radiation heats this mixture, the ice undergoes sublimation, the direct transition from solid to gas without passing through a liquid phase. This sublimating gas carries dust particles away from the nucleus, creating the glowing coma that makes comets visible from great distances. But sublimation requires energy, and in the extreme cold of the outer solar system, there simply shouldn't be enough solar heating to drive significant activity. Water ice, which dominates the composition of most comets, has a sublimation temperature of about minus 78 degrees Celsius at the low pressures found in space. Beyond Jupiter's orbit, surface temperatures on exposed comet nuclei should be around minus 200 degrees Celsius or colder, far too cold for water ice to sublimate at any appreciable rate. The Swift Space Telescope, originally designed to detect gamma-ray bursts from distant galaxies, provided crucial confirmation of the early activity detected by TESS. Swift's sensitive UV and X-ray instruments captured the spectroscopic signature of hydroxyl radicals, OH molecules produced when solar ultraviolet radiation breaks apart water molecules in the coma. The detection of these molecular fragments at such vast distances from the Sun was like finding evidence of a campfire in the middle of Antarctica. Dr. Dennis Bodowitz at Auburn University, who has spent his career studying the interaction between comets and solar radiation, described the early activity of 3I Atlas as unprecedented in the annals of comet science. His team's analysis of the Swift data revealed not just the presence of OH radicals, but their abundance patterns, which suggested that water was being produced at rates that should have been impossible given the available solar energy. The mystery deepened when astronomers compared 3I Atlas's behavior to that of other long-distance visitors. Comet Hale-Bopp, one of the most active comets ever observed, didn't develop a detectable coma until it reached about 13 astronomical units from the Sun, already closer than 3I Atlas when it first showed signs of activity. Even more remarkably, Hale-Bopp was a much larger comet, with a nucleus estimated at 40 kilometers in diameter compared to 3I Atlas's estimated size of just a few kilometers. The size difference makes 3I Atlas's early activity even more puzzling. Smaller nuclei have less gravitational binding energy to hold onto the gas and dust produced by sublimation, and they also have higher surface area to volume ratios, which should make them more susceptible to losing their volatile materials over cosmic time. That a relatively small comet could maintain enough volatile material to produce observable activity at such distances challenges our fundamental understanding of how these objects evolve. Several theoretical explanations have been proposed to account for this anomalous behavior, each raising its own intriguing questions. The most straightforward possibility involves exotic ices with much lower sublimation temperatures than water. Carbon monoxide ice, for example, can sublimate at temperatures as low as -205 degrees Celsius. If 3I Atlas's nucleus contained significant amounts of such supervolatile materials, it might begin outgassing at distances where water ice remains frozen solid. The extreme carbon dioxide abundance revealed by JWST's later observations supports this interpretation. Carbon dioxide ice sublimates at -78 degrees Celsius, making it more volatile than water ice but less volatile than carbon monoxide. A nucleus rich in carbon dioxide ice could reasonably begin showing activity in the outer solar system, though the observed level of activity still pushes the boundaries of what current models predict. Dr. Gal Sarid at the University of Central Florida has developed sophisticated thermophysical models to understand how different ice compositions might affect comet activity at large distances. His calculations suggest that 3I Atlas would need to be composed almost entirely of volatile ices to sustain the observed level of activity at 6.4 astronomical units. This composition would be unlike any solar system comet ever studied, but might be consistent with formation in the extremely cold environment of the interstellar medium. Another possibility involves subsurface heating mechanisms that could drive activity independently of solar radiation. Radioactive decay of elements incorporated into the comet during its formation could provide internal heat sources that remain active over billion-year timescales. While the required concentrations of radioactive elements would be unusual, they're not impossible, particularly for an object that formed in a stellar environment very different from our solar system. The crystallization of amorphous ice represents yet another potential energy source. When water ice forms rapidly in extremely cold conditions, it can exist in an amorphous, glass-like state that contains more energy than crystalline ice. Over long timescales, this amorphous ice gradually converts to the more stable crystalline form, releasing energy in the process. For a comet that had remained in the deep cold of interstellar space for billions of years, this gradual crystallization could provide enough heat to drive sublimation even when solar heating is negligible. Magnetic field interactions offer a more exotic explanation. If 3I Atlas possesses embedded magnetic materials or electrical conductivity, its motion through the Sun's magnetic field could induce electrical currents that generate heat. While this mechanism is typically negligible compared to solar heating, it becomes more important at large distances where solar energy is weak. The possibility of impact heating from interstellar dust has also been considered. During its billion-year journey through space, 3I Atlas would have encountered countless microscopic dust grains traveling at high relative velocities. Each impact would deposit a small amount of kinetic energy as heat, and the cumulative effect over cosmic time might be sufficient to maintain elevated subsurface temperatures. Recent observations have revealed that the early activity of 3I Atlas follows distinct patterns that provide clues about the underlying physical processes. The brightness variations and spectroscopic changes suggest that activity is not uniformly distributed across the nucleus surface, but instead originates from specific active regions that may be exposed to different thermal conditions or have different compositions. Dr. Matthew Knight at the Naval Research Laboratory has been tracking these activity patterns using ground-based telescopes around the world. His observations suggest that the active regions on 3I Atlas may be related to topographical features, perhaps impact craters or structural weaknesses where subsurface volatiles can more easily escape to space. This patchy activity distribution is common among solar system comets, but observing it at such large distances from the Sun provides new insights into the relationship between surface geology and volatile outgassing. The temporal evolution of the early activity has also proved informative. Rather than showing the steady increase in brightness typical of comets approaching the Sun, 3I Atlas has exhibited irregular fluctuations that suggest complex feedback mechanisms between different regions of the nucleus. This behavior might indicate that the early activity is depleting volatile materials from surface layers, gradually exposing less volatile subsurface materials that respond differently to available energy sources. These evolving activity patterns have become even more intriguing as 3I Atlas embarks on what astronomers are calling the most spectacular interstellar flyby in human history, a grand tour of our solar system that brings this ancient visitor closer to multiple planets than any previous interstellar object. The choreography of 3I Atlas's passage through our planetary neighborhood reads like a carefully planned itinerary, though the forces orchestrating this cosmic ballet are purely gravitational. Each encounter has been precisely calculated by orbital dynamicists around the world, creating a timeline of observational opportunities that astronomers have been preparing for with unprecedented coordination and excitement. The first major milestone occurred on October 3, 2025, when 3I Atlas swept past Mars at a distance of just 0.19 astronomical units, roughly 28 million kilometers. To put this in perspective, this is closer than Mars ever comes to Earth during its orbital dance around the Sun. For a brief moment, this interstellar visitor became Mars's closest neighbor, racing past the red planet at a relative velocity of more than 30 kilometers per second. Dr. Frank Marquis at the SETI Institute coordinated ground-based observations of the Mars encounter using telescopes across 3 continents. The goal was not just to track the comet's motion, but to search for any gravitational deflection in its trajectory caused by Mars's modest but measurable gravitational field. Such deflections, while tiny, could reveal important information about the comet's mass and internal structure. The Mars flyby also provided the first opportunity to study 3I Atlas at relatively close range using spacecraft in Mars orbit. The European Space Agency's Mars Express probe, though not designed for comet observations, was able to turn its cameras and spectrometers toward the visitor during its closest approach. These observations, while brief and limited by the spacecraft's primary mission, offered a unique perspective on the comet's coma structure and activity patterns from within the inner solar system. Just 26 days later, on October 29, 2025, 3I Atlas reached perihelion, its closest approach to the Sun. At this point in its trajectory, the comet passed through the space between Earth's and Mars's orbits, reaching a solar distance of approximately 1.4 astronomical units. Here, in the warm embrace of our star, 3I Atlas experienced the most intense heating of its billion-year journey, triggering levels of activity that transformed it from a distant curiosity into one of the brightest comets visible from Earth. The perihelion passage marked a critical test of the comet's structural integrity. Many comets fragment when exposed to the thermal stress of close solar approaches, unable to withstand the rapid heating and gas production that occurs as their ices sublimate en masse. The fact that 3I Atlas survived this thermal assault intact provided important clues about its internal structure and composition, suggesting either a remarkably coherent nucleus or a composition dominated by materials more resistant to thermal stress than typical comet ices. Ground-based telescopes around the world tracked the comet through its perihelion passage with unprecedented detail. The Atacama Large Millimeter Array in Chile captured high-resolution images of the comet's inner coma, revealing jet structures and asymmetries that reflected the uneven distribution of active regions on the nucleus surface. These observations showed that 3I Atlas's activity was indeed concentrated in specific areas, creating fountain-like plumes of gas and dust that gave the coma a complex dynamic structure. 5 days after perihelion, on November 3, 2025, 3I Atlas encountered Venus, passing within the orbit of our sister planet at a distance that brought it tantalizingly close to the second planet from the Sun. While not as close as the Mars flyby, the Venus encounter occurred at a time when the comet's activity had reached peak intensity, creating spectacular observing conditions for both professional and amateur astronomers. The Venus encounter coincided with optimal viewing geometry from Earth, with the comet positioned in the pre-dawn sky as a brilliant beacon visible to the naked eye. Amateur astronomers around the world captured stunning photographs of the comet's tail, now fully developed and stretching across several degrees of sky. These images, shared widely on social media, brought the wonder of this interstellar visitor to millions of people who might otherwise never have looked up at the night sky. Professional observatories used the Venus encounter to conduct detailed spectroscopic studies of the comet's tail composition. The European Southern Observatory's Very Large Telescope in Chile obtained high-resolution spectra that revealed the presence of numerous molecular species in the tail, including water vapor, carbon dioxide, carbon monoxide, and complex organic compounds. These observations provided the most complete chemical inventory of an interstellar visitor ever obtained. The gravitational influence of Venus, while modest compared to that of larger planets, still produced measurable effects on 3I Atlas's trajectory. Precision tracking by radar observatories detected tiny changes in the comet's velocity and direction, providing additional constraints on its mass and helping refine predictions for subsequent encounters. December 19, 2025, brought the closest approach to Earth, a moment that astronomers had been anticipating since the comet's discovery. At a distance of 1.8 astronomical units, roughly 270 million kilometers, 3I Atlas passed closer to our planet than any confirmed interstellar object in recorded history. While still far beyond the orbit of our moon, this distance was close enough to enable detailed studies using Earth's most powerful telescopes. The Earth encounter occurred during the comet's post-perihelion phase, when its activity remained high, but the coma had evolved into a more mature, well-developed structure. This timing proved ideal for studying the relationship between the comet's nucleus and its extended atmosphere. The Hubble Space Telescope captured unprecedented images of the nucleus itself, revealing a dark, irregularly shaped object roughly 3 kilometers in diameter, smaller than many solar system comets, but clearly substantial enough to have survived its billion-year journey through interstellar space. James Webb Space Telescope observations during the Earth encounter provided the most detailed chemical analysis of the comet's composition. The extreme carbon dioxide abundance that had made 3I Atlas so unusual was confirmed and refined, with new measurements revealing subtle variations in the CO2 to water ratio across different regions of the coma. These variations suggested that the nucleus had a heterogeneous composition, with different areas containing different mixtures of ices and rocky material. Ground-based radar observations during the Earth flyby attempted to directly detect the solid nucleus and measure its rotation period and shape. The Arecibo Observatory's replacement facility in Puerto Rico, along with the Deep Space Network's Goldstone antenna in California, transmitted powerful radar signals toward the comet and analyzed the reflected echoes. While the signals were weak due to the comet's distance and small size, the observations provided valuable constraints on the nucleus's physical properties. The final major planetary encounter will occur on March 16, 2026, when 3I Atlas passes within 0.36 astronomical units of Jupiter, roughly 54 million kilometers. This flyby will bring the comet closer to the giant planet than most of Jupiter's major moons, subjecting it to gravitational forces thousands of times stronger than those experienced during its other planetary encounters. The Jupiter encounter represents both the climax and conclusion of 3I Atlas's grand tour. Jupiter's immense gravitational field will act as a cosmic slingshot, accelerating the comet to even higher velocities as it continues its journey back into interstellar space. Calculations suggest that the comet will leave the Jupiter system moving at nearly 50 kilometers per second relative to the Sun, fast enough to escape our solar system's gravitational influence entirely and continue its wandering through the galaxy. The scientific value of the Jupiter encounter extends beyond simple gravitational dynamics. Jupiter's powerful magnetic field and radiation environment will interact with the comet's ionized coma in ways that could reveal important information about the electrical properties of interstellar material. The Juno spacecraft, currently orbiting Jupiter, may be able to detect these electromagnetic interactions and study how interstellar visitors respond to the harsh radiation environment of the outer solar system. Each of these planetary encounters has been carefully orchestrated by the laws of celestial mechanics, but their scientific value depends entirely on the coordinated efforts of astronomers around the world. International collaborations have been established to ensure that every opportunity for observation is maximized, with telescopes in different time zones providing continuous coverage as the comet moves across the sky. The first time the image arrived, it looked almost too delicate to belong to the same universe that builds stars and smashes galaxies together. A pale wisp stretched against the darkness, almost like a brushstroke left behind by an unseen artist. It was Gemini South that delivered it, one of the most capable ground-based observatories we possess, its mirrors tuned to catch faint whispers of light that had travelled millions of miles to reach us. There it was, 3I Atlas, a smudge of eternity drifting across the black canvas of the sky. For astronomers, these images are data points, layers of measurable detail that can be processed, catalogued, compared. Yet for the rest of us, something different happens. We see not just a comet, not just an interstellar object, but something closer to poetry. A tiny alien wanderer, its body wrapped in sunlight, spilling dust and gas into a luminous veil. The sight alone is enough to remind us that our universe, for all its physics and formulas, is also an artist at heart. As weeks passed, Gemini South returned again and again to capture its evolving face. Each new photograph revealed subtle changes like pages in a story still being written. The coma expanded outward, swelling like a breath. At first it was compact, hugging the icy nucleus at its core, but as the sun's light poured over it, the coma began to billow outward, thin but persistent, until it resembled a glowing cocoon floating in space. The tail followed, a filament stretched by solar winds into an ethereal stream. Dust particles and vaporized gases rode the invisible currents, tracing long arcs that seemed to bend the darkness itself. Hubble joined the watch next, its position above Earth's atmosphere giving it a clarity no ground-based telescope can achieve. Where Gemini South painted in broad strokes, Hubble revealed fine detail. It captured delicate layers of structure in the coma, subtle jets of gas, asymmetries in the tail, irregularities hinting at activity beneath the surface. This was not merely an object drifting passively through space. It was alive in its own way, reacting, changing, releasing its secrets into the void. The images glowed in shades of blue and white, almost painterly in their texture, like the flicker of a candle frozen in space. But the true revelation came from the James Webb Space Telescope. With its eyes tuned to infrared wavelengths, JWST sees the universe not as we do, but as it radiates in hidden light. When Webb turned toward Three Eye Atlas, it was as if the veil had been lifted. Suddenly the coma was not just a soft glow, but a detailed map of chemical fingerprints. The extraordinary 8:1 ratio of carbon dioxide to water was not only measured, but visualized in delicate gradients, invisible to our eyes, yet captured by Webb's instruments. These weren't simply pretty pictures, they were coded with information about the comet's birthplace, the ancient conditions under which it formed, the molecular echoes of a star system we may never see. The public reaction was immediate. Social media platforms lit up with posts sharing the images, Gemini's streaks of light, Hubble's crystalline details, Webb's surreal false-color renderings. People compared them to paintings, to dreamscapes, to scenes from films. Hashtags trended across languages and time zones. Teachers downloaded the images to bring into classrooms. Artists reinterpreted them into digital collages and murals. For a brief span of time, an interstellar comet became not just an astronomical object, but a cultural moment, a piece of shared wonder. Yet beneath the flood of aesthetic awe, the scientists worked. Each pixel in those images contained measurements, brightness levels indicating dust density, spectral lines betraying the presence of specific molecules, subtle shifts in the coma's shape hinting at the nucleus's rotation. For the researchers, beauty and science were not separate. They were layered, like a painting that grows richer the closer you look. The outer glow captivated the world, but within it lay the data that could change how we understand comets across the galaxy. It is easy to forget how much effort goes into creating such portraits. The telescopes are not casual photographers snapping pictures on a whim. They are instruments of precision, each exposure carefully calculated, each filter selected to capture a particular wavelength of light. The images we see, the ones shared on screens and news headlines, are often composites, built from multiple frames stitched together, adjusted for contrast, colored to highlight details invisible to human eyes. In a sense, they are collaborations between the universe and us, photons that have traveled across space, interpreted and translated by our technology into something we can not only measure but also marvel at. The coma's growth became a kind of time-lapse performance. Early in its journey inward, the glow was faint, like the halo of a lantern glimpsed through fog. But as Three Eye Atlas drew closer, the coma thickened, expanding tens of thousands of kilometers across, enveloping the tiny core at its heart. Astronomers compared it to a living organism, exhaling as it approached the sun, the tail lengthened, streaming away in delicate strands. Solar radiation pressure sculpted it into shapes that seemed almost organic, twists, bends, fans of dust drifting outward. For some observers, it looked like a ghostly ribbon unfurling across the stars. For others, it resembled a painter dragging a brush through liquid light. What captivated so many was not just the scale, but the realization of what these images represented. This was not a native child of our solar system. This was an emissary from somewhere else, a fragment of another star's creation drifting through our backyard. To see its portrait in such detail was to hold in our gaze a piece of the unimaginable, a world we will never visit, distilled into the dust of a comet, now lit by our own sun. Every pixel was, in a sense, a handshake across interstellar space. On social media, comparisons flourished. Some called it a cosmic flower blooming against the night. Others saw a ghost ship adrift in the sea of stars. The metaphors were endless, each an attempt to capture in language what the eye already knew. That here was beauty uninvited, beauty unexplainable, beauty that arrived from beyond the borders of our home. Yet within scientific circles, the focus sharpened on the details hidden in those graceful forms. The distribution of brightness across the coma revealed the uneven release of gases from the surface. Jets spiraled outward, faint but detectable, suggesting the nucleus was rotating irregularly. The tail's structure recorded the push and pull of solar wind interacting with the escaping material. By comparing images from Gemini South, Hubble, and JWST across time, astronomers could build dynamic models of the comet's behavior, reconstructing not only what we saw, but why we saw it. It is here, in this overlap of art and science, that the story becomes most compelling. For the public, the comet's beauty is reason enough to look up. For the scientists, its beauty is inseparable from its physics. Each curve, each shimmer, each expanding veil is evidence, a clue in the cosmic detective story. To admire the image is to step into the same space as the astronomers themselves, who find wonder not despite the data, but within it. In classrooms around the world, children saw the pictures projected on screens. Some of them had never looked through a telescope, never traced constellations across the night sky. Yet here was a visitor from another star, its image shared across continents, sparking the kind of curiosity that no textbook alone could ignite. Artists painted it, poets wrote about it. Amateur astronomers went outside, inspired to search the skies themselves. For a moment, the divide between science and culture blurred, replaced by something older and more universal, the simple act of wonder. The images themselves continued to evolve, not only because the comet changed, but because the technology observing it did. Filters shifted, exposures lengthened, instruments recalibrated. Each new release brought fresh details, faint arcs of dust trailing behind, subtle color differences hinting at complex chemistry, structures in the coma that seemed to ripple like fabric caught in a breeze. It was as if the comet had become a gallery with rotating exhibitions, each one offering a new angle, a new interpretation, a new revelation. Perhaps the most remarkable part was how accessible it all became. Only a few decades ago, such images would have circulated slowly, buried in academic journals, seen only by specialists. Now they spread instantly, appearing on phones, laptops, and giant screens in public squares. Humanity watched together as the comet's portrait unfolded, millions of people across the world witnessing the same visitor at the same time. In a way, the comet had become a shared human experience, an art show staged on the stage of the universe, with the audience stretched across the globe. Yet no matter how widely shared, the images retained their mystery. To look at them was to realize how little we truly know. Each new frame carried not only beauty, but questions. Why was this interstellar object so unusually rich in carbon dioxide? Why did its activity begin so early, long before most comets awaken? How did its structure remain intact against stresses that should have torn it apart? The images did not answer these mysteries, but they gave them form. They turned abstract scientific puzzles into something visible, something we could all look at and feel in our bones. So, as Gemini South, Hubble, and JWST continued their watch, the comet transformed before our eyes, not into something familiar, but into something both alien and intimate. Alien, because it was born in a place we will never see. Intimate, because now we had its portrait, glowing faintly but defiantly against the darkness, a reminder that the universe's most profound truths are often also its most beautiful. It was in this balance, between aesthetics and evidence, between wonder and analysis, that the comet lived in human imagination. A gallery of cosmic art, unfolding one image at a time, shared across screens, discussed in papers, printed on posters, carved into memory. Each photograph was both an answer and a question, both a piece of data and a work of art. Each one carried us deeper into the mystery, preparing us for the next revelation waiting just beyond the horizon of discovery. For all the beauty we've seen in its glowing coma and sweeping tail, Three-Eye Atlas carries within it an even deeper mystery, one written not in light but in endurance. Because while comets are among the most fragile travelers in the solar system, prone to crumbling under the stress of their journeys, this interstellar visitor has refused to break. It has raced past planetary giants, felt the pull of gravity twist its path, endured the heat of the sun pressing down on its icy surface, and yet it holds together. No great fractures, no dramatic splitting into smaller shards, no collapse into a trail of debris. It survives, intact, as if built with a strength no ordinary comet should possess. Astronomers know this story well in other comets. Many of our local icy wanderers cannot endure the pressures of their close encounters with the sun. They shatter spectacularly, their dusty remains scattering into glowing clouds that drift apart like ashes on a cosmic breeze. Comet Shoemaker-Levy 9 famously broke apart into more than 20 pieces before slamming into Jupiter in 1994, each fragment burning like a scar across the planet's atmosphere. Comet Elenin disintegrated into a ghostly haze as it neared the Sun in 2011, never to be seen again. Even bright, celebrated comets often leave behind trails of fragments when solar heat or gravitational tides prove too much for their brittle structures. Yet Three-Eye Atlas resists. Despite passing within reach of planetary giants, despite bathing in solar radiation powerful enough to boil away surface layers, its nucleus appears unbroken, its core seemingly undisturbed. This resilience stands in stark contrast to what our own solar system's comets usually display. What could explain such an unlikely survival? The leading theories begin with structure. Most comets are thought to be rubble piles, loosely bound collections of ice, dust, and rock clumped together without much internal cohesion. They are like cosmic snowballs, held more by gentleness than by strength. Heat penetrates their surfaces, pressure builds, cracks form, and the weak bonds between their components give way. But if Three-Eye Atlas has endured billions of years adrift in the galaxy, buffeted by radiation, collisions with interstellar dust, and the gravitational tugs of countless stars, perhaps it could not afford to be fragile. Perhaps only the most resilient objects ever survive long enough to reach us. Some astronomers suggest its nucleus must be denser than typical comets, a compact core of ice and rock bound tightly together. Instead of a snowball, it might be closer to stone, forged under different conditions in a foreign star system. If its material froze at higher pressures or incorporated exotic ices less prone to sublimation, the comet's interior might act as a shield, protecting it from the stresses that would tear others apart. Imagine a fortress of frozen chemistry, a wall of durability built in a time and place we can scarcely imagine. Others consider the possibility that its surface has developed a hardened crust over eons of exposure to cosmic rays and micrometeorite impacts. This outer layer could act like armor, sealing the more volatile interior beneath. In this view, Three-Eye Atlas wears a scarred shell, built not in a single moment, but through billions of years of wandering. The shell would vent gases through cracks and fissures, producing the coma and tail we observe, but the deeper core would remain solid, untouched by destructive forces. In effect, the comet would be self-armored, wrapped in a protective skin of its own ancient history. There is also the matter of scale. Some estimates suggest the nucleus of Three-Eye Atlas could be larger than that of many typical comets we've studied. Size brings stability. A bigger nucleus can absorb stresses that would obliterate a smaller one. The forces that rip fragile comets apart might cause only surface shedding here, with the bulk of the body left intact. Like a mountain weathering storms where a pebble would wash away, Three-Eye Atlas persists, its mass alone a form of protection. The implications of this resilience stretch far beyond curiosity. If 3I Atlas truly represents a class of interstellar comets that are tougher, denser, or more durable than those born in our own solar system, then our picture of cometary diversity must expand. It suggests that the architecture of distant planetary systems might produce objects very different from our own. Comets built not as fragile snowballs, but as cosmic survivors hardened against the long, harsh journey between stars. Consider what that means. A body formed billions of years ago in a cradle of starlight far from our own, flung outward by the gravity of giant planets or the collapse of its home system, cast into the interstellar dark. For eons it drifts, colliding with nothing, freezing in the vacuum while stars and galaxies move around it. Yet, through all of this, it endures. Now it races past our sun, carrying the strength of its survival with it. If fragility was ever part of its nature, it was shed long ago. What remains is something extraordinary, a traveler forged by endurance, a relic of resilience. Astronomers speak of it almost with reverence, calling it a cosmic survivor, built to last the ages. The phrase is not poetic exaggeration, but recognition of reality. Every close approach it makes without breaking apart is a lesson in what matter can endure when shaped by alien conditions. Every photograph of its intact core is a reminder that strength itself is a kind of information. Its survival is not only a triumph of luck, but of composition, a silent testimony from another world written in its structure. The thought is almost unsettling. A comet that has seen more of the galaxy than any spacecraft we have ever built, one that has outlived countless stars, holding itself together while time erased entire systems around it. Its nucleus may contain chemistry older than our solar system, but its persistence, the simple fact of still being here, may be the greater marvel. For scientists, this durability offers opportunity. A fragmenting comet complicates observation, its debris cloud scattering signals and disrupting measurements. But a stable, intact nucleus provides a consistent target, a reliable source of data. Instruments can track changes in the coma and tail, without worrying that the source itself has disintegrated. The mystery of its resilience, paradoxically, becomes the reason we can study it so clearly. Yet questions persist. What is the exact density of its core? What combination of ices and minerals produces such strength? Could there be exotic compounds unknown in our solar system, binding its structure tighter than anything we've seen before? Might its interior be layered, compressed like ancient rock strata, hardened by pressures beyond our imagination? Theories circle, but direct answers remain just out of reach, hidden beneath the glowing veil of its coma. In a way, 3I Atlas is a paradox. It behaves like a comet, releasing gases, growing a tail, yet refuses the fragility we associate with cometary bodies. It is a reminder that our categories are provisional, our expectations shaped by what we know of our own small system. Beyond our borders, the rules may bend. What we thought was typical may in fact be only local custom, not universal law. So the interstellar visitor presses on, whole and unbroken, carrying the mystery of its integrity like a secret. Its survival forces us to reconsider not only comets, but the broader story of matter itself, what it can become, what it can withstand, how it can endure the silent violence of the cosmos for billions upon billions of years. The puzzle of its structure is not a minor curiosity, it is the foundation of its identity, the very reason we are able to witness it now. As it arcs past the sun and continues its journey outward, we will keep watching, waiting to see if it finally cracks, if its surface gives way, if its ancient body begins to splinter under stresses yet to come. But so far, it has given no sign of weakness. So far, it seems to carry on, stubborn and whole, as though sculpted with an intent to last. A survivor among the fragile, a fortress among the ruins of rubble piles, a relic built to endure. It moves now toward the next stage of its dance through our solar system, still intact, still mysterious, still carrying the lessons of strength we have yet to decode. To look at 3i Atlas is to glimpse not only resilience, but inheritance. Its survival tells us it is strong, but its chemistry tells us where that strength was born. Locked within its dust and ice are stories of another star system, written in isotopes and elements, waiting for us to decipher. Every fragment that escapes into the coma, every particle carried away in its luminous tail is a messenger from an alien birthplace. For scientists, this is the true treasure, a sample of matter forged beneath a sun that is not our own. When astronomers speak of comets, they often describe them as time capsules. Our local comets are remnants of the early solar system, frozen archives of the conditions that prevailed more than 4.5 billion years ago. They carry the fingerprints of the nebula that collapsed to form the Sun and its planets, untouched by the violent recycling processes that reshape planets and moons. But interstellar comets elevate this idea to another level. They are not just archives of one world, but of another star's creation. They are time capsules from foreign nurseries, each one a direct link to planetary systems far beyond our reach. The isotopic ratios within 3i Atlas matter profoundly. Ratios of hydrogen to deuterium, of carbon isotopes, of oxygen isotopes. These subtle signatures reveal the conditions of temperature, pressure, and chemical abundance in the comet's birth environment. If they differ significantly from what we observe in comets of our own solar system, they become proof that not all planetary nurseries are alike. Each star system may write its own story in chemistry, leaving its signature in the matter it ejects. By studying these fingerprints, astronomers begin to build a comparative science of worlds we cannot visit. Already, 3i Atlas has surprised us with its extraordinary chemistry. The 8:1 ratio of carbon dioxide to water in its coma defies expectations. In our solar system, water dominates cometary compositions. Here, the opposite is true. Such a difference suggests that its birthplace was colder, richer in carbon dioxide ice, or deprived of liquid water during its early history. It hints at protoplanetary disks with different temperature gradients, different distributions of volatiles, different stories of planet formation. Each particle escaping from 3i Atlas carries evidence of that alien past, each molecule a fragment of another system's autobiography. The rarity of this opportunity cannot be overstated. Interstellar visitors are astonishingly scarce. In all of human history, we have confirmed only 3. Oumuamua in 2017, Borisov in 2019, and now Atlas in 2025. That is 3 in the span of modern astronomy across centuries of sky watching. The odds of such objects passing close enough for study are vanishingly small. To have one within reach of our most advanced telescopes, at a time when instruments like JWST are operational, is a convergence of luck and timing that borders on miraculous. Consider Oumuamua. It arrived suddenly, an elongated shape tumbling through space, devoid of the glowing coma that makes comets so visible. Its lack of activity made it difficult to study, and by the time we turned our instruments toward it, it was already fleeing, its secrets receding into the dark. Then came Borisov, an active comet with a tail, offering clearer evidence of interstellar chemistry. Its water content, carbon monoxide abundance, and dust properties revealed a world similar to, yet distinct from, our own comets. Together, these 2 first visitors showed us variety, one barren and enigmatic, the other active and familiar yet still alien. Now Atlas expands that spectrum. It is both active and stable, both chemically strange and structurally resilient. It offers a third data point, a new entry in our growing ledger of interstellar knowledge. With each visitor, the picture grows sharper. We begin to sense patterns, not from one isolated object, but from a comparative gallery. Each comet is a word in a sentence, each sentence part of a story that spans the galaxy. The scientific value of such objects is immeasurable. They allow us to test theories of planet formation, not only in our own neighborhood, but across the Milky Way. For decades, we have modeled protoplanetary disks in computer simulations, guessing at how planets assemble around newborn stars. But simulations are only as good as their evidence. Interstellar comets are evidence, real samples of material shaped by those processes. They tell us whether our solar system is typical or whether it is an exception. They show us what is common in planetary chemistry and what is rare. For example, if multiple interstellar comets show unusually high levels of carbon dioxide compared to water, we might infer that many planetary systems form in colder regions of their disks, or that carbon dioxide ices are more stable in environments unlike our own. If isotopic ratios vary wildly between interstellar objects, it would suggest a rich diversity in star system environments, a galaxy where every nursery writes a different chemical script. If, however, those ratios cluster around similar values, we might find reassurance that the building blocks of planets, and perhaps of life, are more universal than we feared. The challenge lies in measurement. No spacecraft has yet intercepted an interstellar comet, so our data comes from afar. Spectral signatures captured by telescopes, brightness variations mapped against time, outgassing rates measured from the changing coma. These indirect methods require precision, but they are astonishingly powerful. From photons alone, scientists can reconstruct the chemistry of an object billions of kilometers away. Every spectrum collected is another page in the archive of alien worlds. It is not lost on scientists that we are, in a sense, building the first library of interstellar knowledge. Oumuamua, Borisov, Atlas, 3 books on the shelf, each different in style, each written in the language of dust and ice. The library is small now, but with time, it may grow. Surveys like the Vera C. Rubin Observatory, set to begin its all-sky operation soon, are expected to reveal many more interstellar visitors. The galaxy is full of wanderers, and we are only just learning how to see them. Each new discovery will add to the archive, expanding our understanding of planetary diversity across the stars. But even 3 entries are enough to shift our perspective. Imagine if the only knowledge we had of planets came from Earth, and then suddenly we discovered Mars and Jupiter. 2 more worlds would transform our view of what a planetary system can be. That is what these 3 interstellar comets represent for cometary science. They are the first glimpses of a larger family, the first hints of diversity that stretches far beyond our home. The notion of touching matter from another star system carries a kind of quiet awe. To know that the photons bouncing from Atlas's coma into our telescopes are revealing molecules that condensed billions of years ago under an alien sun, it is almost intimate. We are tracing the breath of another world. We are analyzing its stardust, as though reading a letter sent across light years. It makes the galaxy feel less abstract, less remote. For in these particles, we are connected to places we cannot see, to stars we may never visit. The implications extend into the search for life. If interstellar comets carry organic compounds, as many of our local comets do, they hint at the possibility that prebiotic chemistry is widespread in the galaxy. Some scientists even speculate that such comets could serve as delivery systems, scattering organic molecules across interstellar distances. If so, every interstellar comet we study is not just a geological curiosity, but a piece of the puzzle of life itself, a clue to whether the chemistry of biology is unique to Earth or universal across the stars. Each observation brings us closer. High-resolution spectra from JWST reveal faint molecular bands invisible to ground-based telescopes. Dust captured in the comet's tail shows grain sizes and structures, telling us about the conditions under which they formed. Changes in brightness track rotation rates, giving us insight into the dynamics of the nucleus. Even the absence of certain molecules is telling, highlighting what was missing in the comet's birth environment. Piece by piece, the profile sharpens. The picture grows clearer. Yet clarity does not erase wonder. If anything, it deepens it, because each revelation carries another question. Why so much carbon dioxide? Why such structural resilience? What does it mean that three interstellar visitors, each so different, have all found their way into our sight in just a few decades? Is it coincidence, or a glimpse of a much larger population moving silently through the galaxy? Perhaps one day, a spacecraft will meet one of these wanderers up close, sampling its dust directly, drilling into its core, bringing fragments back to Earth. Until then, we work with light, with spectra, with images, but even that is enough to open windows into alien worlds, enough to let us glimpse the chemistry of suns that rise and set far beyond our own. Each interstellar comet is a shard of another place, a piece of a story written elsewhere, arriving like a message carried on the galactic tide. And as Atlas continues on its path, trailing its ancient stardust behind, we will keep reading, keep analyzing, keep listening to the whispers of its alien past. Because this is what it offers us, a fleeting but priceless chance to study matter not from here, but from there, from beyond, from the far reaches of the Milky Way itself. Light alone cannot tell its story without instruments to catch it. As 3i Atlas drifts across the heavens, it is the tools we have built, the telescopes, the algorithms, the networks of watchers that transform its faint glow into knowledge. Without technology, this alien wanderer would be just another flicker lost in the deep black. With it, the flicker becomes a revelation. It began with the Atlas Survey System, a project designed not for cosmic romance, but for planetary defense. Atlas, short for Asteroid Terrestrial Impact Last Alert System, was built to scan the skies for hazardous objects that might come too close to Earth. Each night, its twin observatories sweep wide arcs of sky, photographing stars, galaxies, and any small intruder moving against the background. What sets Atlas apart is automation. Advanced software combs through the flood of images, comparing night against night, teasing out anything that shifts position. Most detections turn out to be asteroids, satellites, or noise. But in early 2025, something unusual appeared. A faint traveler with a trajectory too sharp to be bound by the sun. The algorithms flagged it. Astronomers checked the data. Its orbit was hyperbolic, an unmistakable sign of interstellar origin. Without Atlas's vigilance, it might have slipped by unnoticed. Another anonymous streak on a sensor, but automation caught it, flagged it, and passed the signal on. The system that was built to protect us from incoming rocks instead delivered us a gift from the stars. Discovery is only the beginning. To understand what Atlas was, the world's telescopes turned their eyes toward it. Some of the first were ground-based observatories scattered across the globe. From Chile to Hawaii, from the Canary Islands to South Africa, networks of telescopes coordinated to follow the faint smear across the night. The Earth itself became a platform, its scattered observatories forming a web of vision. Together they tracked the comet's motion, refined its orbit, measured its brightness. With each observation, the shape of its journey grew clearer, the confidence in its interstellar origin more certain. Such coordination is only possible because of advances in orbital mechanics. A century ago, calculating the path of an object across the sky required human computers bent over paper, tracing curves by hand. Today, astronomers use sophisticated algorithms to fit orbital models within hours of detection. With data points from multiple telescopes, they can compute precise eccentricities, velocities, and trajectories. In the case of 3i Atlas, those calculations quickly revealed an eccentricity greater than 1. The unmistakable signature of a hyperbolic path. The numbers confirmed what the eyes suspected. This comet came from beyond. Then the James Webb Space Telescope entered the story. Floating 1 million miles from Earth, shielded by its vast sunshade, JWST brought infrared eyes sharper than any instrument before it. Where ground-based telescopes saw light blurred by atmosphere, Webb saw with clarity. It could dissect the comet's coma in detail, analyzing the faint fingerprints of molecules radiating in infrared. Through its instruments, the shocking 8:1 carbon dioxide to water ratio came into view, a measurement impossible without its sensitivity. JWST was not just photographing the comet, it was peeling back its layers, translating invisible radiation into chemical truth. In many ways, Webb was the perfect partner for an interstellar visitor. Its design was meant to probe the earliest galaxies, to study the atmospheres of exoplanets, to trace the faintest heat from stars at the edge of time. Yet here it was, turning those same tools toward a passing comet, uncovering chemistry that rewrote what we thought possible. It was a reminder that technology built for one purpose can often reveal wonders in another, that a telescope's greatest discoveries are often the ones no one predicted. But Webb was not alone. Hubble still played its role, capturing high-resolution images in visible light. Gemini South provided repeated ground-based views, watching as the coma expanded. Radio telescopes scanned for emissions from molecules like OH, the fingerprints of water broken apart by sunlight. Each instrument added a layer, like different brushes painting the same portrait. Alone, none could capture the whole. Together, they gave us a mosaic of understanding. Behind the scenes, an invisible collaboration was unfolding. Data streamed across continents, from observatory servers to research teams, from professionals to amateurs. Citizen scientists played their part too. In the age of digital astronomy, skilled amateurs with powerful backyard telescopes can contribute real observations, feeding positional data into networks like the Minor Planet Center. These contributions refine orbital models, extend tracking, and sometimes even catch changes professionals miss. In the case of interstellar visitors, every observation matters. Their paths are brief, their opportunities fleeting, and the more eyes watching, the clearer the picture becomes. Such collaboration is global by necessity. No single telescope can track a comet across an entire orbit. The Earth turns, skies cloud, instruments need rest. But a telescope in Chile can hand the baton to one in Hawaii, which can then pass it to a station in Australia, which returns it to South Africa. The comet never leaves view for long. The planet becomes a single, coordinated observatory, a world-spanning machine built of human effort and technological vision. The speed with which information flows today is as crucial as the telescopes themselves. The moment Atlas flagged the object, alerts spread across databases, mailing lists, online platforms dedicated to astronomical discovery. Within hours, researchers around the globe knew a new interstellar visitor was here. They mobilized, pointed their instruments, and began to record. In an earlier age, days or weeks might have passed before word spread. By then, the opportunity could have been lost. Now, discovery and observation are nearly simultaneous, a choreography of science enabled by global communication. What emerges from this network is more than data. It is a sense of collective witness. Astronomers in different hemispheres, speaking different languages, working under different skies, are all part of the same effort. They share plots of brightness curves, orbital fits, spectra of molecular lines. They debate interpretations, refine models, propose hypotheses. Science is not a solitary pursuit, but a chorus, each voice adding to the harmony. 3i Atlas is not the achievement of one observatory or one nation. It is the achievement of a planet that has learned how to watch together. This is what makes interstellar visitors so extraordinary. They demand the full extent of our technological and social capacity. To capture them, we must use automated surveys, advanced space telescopes, global ground networks, citizen contributions, instant communication. They are fleeting, unpredictable, and rare, and only a united web of technology and collaboration can hold them long enough for study. Each new visitor tests not only our instruments, but our ability to act as a species, to marshal our tools in time to catch the messenger before it is gone. Consider what would have been missed without this collaboration. Without Atlas's automation, the object might never have been flagged. Without ground-based networks, its orbit might not have been refined. Without JWST, its chemistry would remain a mystery. Without citizen observers, its path might lack crucial data points. It is not any one tool, but all of them working in synchrony that reveal the truth. Technology is the bridge between the faint streak of light in the sky and the profound knowledge it carries. As 3I Atlas moves further through our solar system, the network continues to follow. Each telescope adds fresh measurements, each algorithm updates its orbit, each observation deepens the portrait. It is an ongoing act of revelation, a partnership between human curiosity and the tools we have built to extend our sight. The comet gives us its light, but only technology transforms that light into meaning. And so, in the glow of screens filled with spectral lines, in the hum of servers crunching orbital fits, in the silent watches of telescopes under distant skies, the story of 3I Atlas unfolds. It is a story written not only by the comet itself, but by the instruments that see it, the networks that connect them, and the people who have chosen to look up together. The question that lingers now is what this collaboration points toward, what possibilities lie beyond mere observation, what new frontiers our technology might open as we chase these wanderers deeper into the dark. The question that lingers is not only how we watch these wanderers, but whether we could ever reach them. Observing from afar is one kind of triumph. Sending something to meet them face to face would be another. When astronomers plot the trajectory of 3I Atlas, the numbers carry both wonder and frustration. It is here, within our reach, in the sense that it shines in our skies, yet untouchable, slipping past on a path too swift for our rockets. To look upon it is to feel the gap between what we can see and what we can touch. The challenge is speed. 3I Atlas, like Oumuamua and Borisov before it, races on a hyperbolic course, cutting through the solar system at tens of kilometers per second. By the time we notice such objects, they are already inbound, already plunging toward their brief encounter with the sun. Designing a spacecraft to catch them is like asking a sprinter to chase a bullet in mid-flight. The physics is merciless. Our most powerful launch systems, even when paired with clever gravity assists, cannot match that pace on short notice. This is why the idea of readiness becomes so important. Rather than waiting for a visitor and scrambling to respond, some propose building interceptors in advance, craft stored in space, fueled and poised, ready to launch the moment an alert arrives. These would not need to guess where to aim years ahead of time. They could be directed once the path of an interstellar visitor is certain. It is a logistical dream with immense technical demands, yet it embodies the spirit of seizing fleeting chances. Among the boldest visions for interstellar pursuit is breakthrough starshot, a concept born not for chasing comets, but for reaching the stars themselves. Starshot imagines fleets of tiny probes, each no larger than a microchip, pushed to near-light speeds by powerful Earth-based lasers striking reflective sails. The goal is Proxima Centauri, 4 light-years away, reached in just a few decades. If we can send such probes outward, some wonder if we might also use the idea closer to home, deploying laser-driven sails not to cross interstellar gulfs, but to hurl interceptors toward interstellar visitors passing through. The lessons from 3I Atlas sharpen these questions. Its unusual chemistry, its stubborn integrity, its early activity far from the sun, all are details we only know from a distance. Imagine holding a fragment in our hands, a physical sample of matter from another star system. The potential for science is staggering. isotopes that could reveal conditions in alien nurseries, minerals forged under foreign suns, structures that record histories unlike any in our solar system. But to reach such material requires speed, precision, and foresight that push our technology beyond its current edge. Designing for this challenge forces a new kind of thinking. Spacecraft meant to chase an interstellar comet cannot rely on leisurely decades of cruising like Voyager or New Horizons. They must accelerate fast, endure long exposures to radiation, and carry instruments compact enough to survive high-velocity encounters. Some propose flyby missions, in which a probe streaks past the object in hours, snapping images and collecting spectra before vanishing into the dark. Others dream of more ambitious rendezvous, in which a craft slows enough to travel alongside the wanderer, studying it for months. The latter feels almost impossible with current propulsion, but impossibility has never stopped human imagination from sketching paths toward the future. Future telescopes will be critical in shaping these attempts. The Vera C. Rubin Observatory, expected to begin operations soon, is designed to survey the entire southern sky repeatedly, building an ever-updating atlas of moving objects. Its sensitivity and wide field of view make it a prime tool for detecting interstellar visitors earlier, when they are still inbound, when there is still time to plan. A discovery made years before perihelion, rather than months, could change everything. It could transform a hopeless chase into a feasible mission. Other space-based telescopes, conceived with planetary defense in mind, may also prove invaluable. Missions like NASA's NEO Surveyor, designed to spot potentially hazardous asteroids using infrared, will also sweep up faint interstellar candidates. With each new set of eyes on the sky, the odds increase that we will find the next wanderer sooner, giving engineers precious lead time. Speculative mission concepts proliferate in this climate of possibility. Some envision hybrid missions in which a spacecraft launched to intercept a distant asteroid could pivot toward an interstellar object if one appeared. Others suggest modular spacecraft with interchangeable propulsion stages, adaptable depending on the target's trajectory. More futuristic proposals lean on nuclear propulsion, solar electric engines, or even experimental fusion systems to achieve the rapid acceleration required. Each idea carries its own risks and challenges, but all share a common dream: closing the distance between us and the alien stones that pass through our skies. The pursuit of such visitors is not only about exploration, but about perspective. To touch matter from beyond the sun is to collapse the gap between stars, to bring into human hands the raw material of other worlds. It is a way of expanding science without leaving the solar system, a shortcut to interstellar sampling missions that would otherwise take millennia. In this sense, 3i Atlas and its kin are like couriers, delivering to our doorstep what we cannot yet fetch ourselves. Building the capability to meet them halfway is an act of seizing destiny. The difficulties, of course, remain immense. Engineers debate whether intercepting such fast-moving targets is worth the enormous cost, whether resources might be better spent on telescopes that can watch from afar. But history suggests that where there is vision, persistence follows. The same skepticism once greeted the Apollo program, the Mars rovers, the Webb telescope itself. What was once dismissed as impractical can, within a generation, become reality. The growing archive of interstellar visitors fuels this momentum. With each detection, with each mystery revealed, the case for direct exploration grows stronger. A library of chemical profiles, orbital histories, and physical behaviors is being built. Every new entry sharpens our sense of what is possible, what is rare, and what might be discovered if we could only touch the source. The argument writes itself. The sky is offering us samples from other star systems. All we need is the courage and the tools to collect them. In this way, 3i Atlas is not just a comet, not just a curiosity. It is a challenge thrown down by the universe, a moving target daring us to try. Will we rise to it? Will the next generation of scientists and engineers design the craft that finally meets such a wanderer face to face? The answer may determine not only how we study these visitors, but how we prepare for journeys far beyond. Because in chasing them, we practice for larger ambitions. The technology that might one day let us rendezvous with a comet from another star is not so different from the technology that might one day send us to those stars themselves. Each pursuit teaches us about propulsion, navigation, communication across vast distances. Each attempt nudges us closer to the long-dreamed future in which interstellar space is not a barrier but a frontier. So when 3i Atlas fades from our skies, when it slips back into the void that birthed it, the question will remain burning in those who watched. How do we ensure that the next time we are ready? What must we build? What must we dare to catch the messenger rather than watch it pass? The comet carries no answers, only the silent invitation to follow. And it is an invitation humanity is beginning to take seriously, one mission concept, one telescope, one dream at a time. How do we ensure that the next time we are ready? That question hovers over every image of 3i Atlas, but behind it lies another, quieter one. Even if we were ready, do we truly understand what we are looking at? The comet's behavior has been like a puzzle with missing pieces, each observation answering one riddle while creating two more. The chemistry is perhaps the most jarring, a carbon dioxide to water ratio so skewed, so unlike any cometary balance we have seen before, raises questions that spread outward like ripples on a pond. If 3i Atlas carries such unusual chemistry, then where did it form? Did it condense in a region of its birth system where carbon dioxide ice was abundant, or does its composition reflect some catastrophic reshaping long after formation? The answer matters because every comet is a frozen record of its origin. Studying them is like peering into the planetary nursery from which they came. If this comet is the message in a bottle, what exactly is the story sealed inside? Its activity poses another conundrum. Astronomers expected a visitor from the cold to awaken closer to the sun, but 3i Atlas was already stirring far out at 6.4 astronomical units. Out there, sunlight is weak, warmth barely more than a whisper. Why would gases sublimate so far from the furnace? Is there some volatile material hidden within, more eager to vaporize than the ices we are used to? Or is the comet's structure itself somehow designed, or perhaps evolved through survival, to vent earlier than expected? The physics of sublimation cannot be cheated, so perhaps our models are incomplete. Even its durability refuses to fit the script. We have seen comets fall apart under less stress. We have watched fragile nuclei fracture, dissolve into fragments, vanish into dust. Yet this visitor holds together, a cosmic survivor built to last the ages. Its persistence demands an explanation. Does it have a dense, rocky interior unlike our fluffy solar comets? Is it held by an icy shell compressed through eons of exposure? Or is there some entirely unknown structure that grants such improbable strength? In asking these questions, we are forced to reconsider what a comet even means. These mysteries stretch beyond a single object. They challenge comet science itself. For decades, researchers have studied our own solar system's comets, building models of how they form, how they behave, how they evolve. 3i Atlas, like Oumuamua and Borisov before it, throws those models into disarray. It is not enough to study our local family. The galaxy is filled with strangers, each carrying a different history, shaped by different suns, sculpted by different gravitational dances. Perhaps our theories are too parochial, too centered on one star and its planets. Perhaps the true diversity of comets is far broader than we have imagined. This possibility leads to another haunting thought. How many more of these travelers are out there unseen? If 3 have already passed within a short span of years, what does that say about the invisible tide beyond? Statistically, interstellar objects must be common. Billions, perhaps trillions, drift through the galaxy, each one a cast-off from some planetary system's birth. Our solar system is not isolated, but immersed in a steady rain of alien debris. Most are too small or too faint to notice, slipping past unmarked. How many pass each decade, each year, just beyond the limits of our detection? New surveys may provide answers. The Vera C. Rubin Observatory promises to map the sky with such depth and regularity that interstellar visitors will be revealed more often. Some estimates suggest one could be detected every year or two once Rubin is fully operational. If so, we are at the beginning of a golden age of discovery, where the rarity of Oumuamua will be replaced by the familiarity of a whole class of objects. Yet with familiarity comes a deeper challenge. How do we make sense of the diversity they will show us? Each interstellar visitor carries implications for planetary system formation. If 3I Atlas is rich in carbon dioxide, perhaps its home system produced planets very different from ours, with chemistry skewed toward volatiles we rarely see in such abundance. If Oumuamua's strange shape and acceleration hint at something non-cometary, perhaps planetesimals in other systems evolve along paths our models have never considered. Every visitor is a test of our theories, a reminder that what seems universal may only be local. The laws of physics do not change, but the outcomes of those laws can vary in ways our imaginations have not yet encompassed. Beyond science lies philosophy. To gaze upon 3I Atlas is to confront time and distance on a scale that stretches human comprehension. This comet may have formed before Earth itself existed, born in a system whose star has long since died. It has wandered for billions of years, silent and unseen, until now, when it passes within our sight. What does it mean for us, fragile beings bound to a single world, to catch a glimpse of such endurance? In the glow of its coma, we see not only chemistry and physics, but also a mirror held up to our own place in the cosmos. There is humility in this realization. We often think of ourselves as explorers, as pioneers pressing outward, yet in truth, the galaxy has been sending emissaries to us all along. These comets, these wanderers, are reminders that we are not alone in space, not in the sense of life, though perhaps one day that too, but in the sense of shared material existence. The galaxy is porous. The boundaries between systems are not walls, but doorways, crossed by dust, by rocks, by frozen bodies carrying the fingerprints of distant suns. To study them is to study the unity of the Milky Way itself. For some, this raises unsettling possibilities. If interstellar comets can reach us, so too could other things, fragments of planets, debris from ancient collisions, even perhaps artifacts of civilizations. Avi Loeb's suggestion that Oumuamua might be artificial was controversial, even polarizing, but it tapped into a deeper unease. How do we know what is natural and what is not, when our sample size is so small? How can we be sure we are not overlooking something extraordinary by forcing it into familiar categories? Each interstellar visitor confronts us not only with data, but with the limits of our imagination. The mysteries of 3I Atlas highlight this tension. Its composition, its durability, its activity, all strain at the edges of explanation. Astronomers produce models, refine equations, simulate scenarios. Yet each solution seems provisional, temporary, waiting for the next observation to undo it. This is the rhythm of science, but it feels different here because the stakes are cosmic. To misunderstand a local comet is one thing. To misunderstand an interstellar one is to miss a message carried across eons, a message we may never receive again. Still, the very act of asking these questions deepens our perspective. Perhaps the value of 3I Atlas is not only in what it reveals, but in what it forces us to confront. The gaps in our knowledge, the assumptions we hold, the fragility of our models. To see a mystery and admit we cannot yet solve it is not failure, but the beginning of wisdom. These comets remind us that the universe is larger, stranger, and more various than any single theory can capture. The questions multiply. How many planetary systems shed material like this? How much of the galaxy's interstellar medium is seeded with such debris? Could the chemistry of interstellar comets have played a role in the origins of life, not only here, but elsewhere? Do these visitors carry ingredients that might have rained down on young worlds, altering their histories forever? The implications stretch beyond astronomy into biology, into philosophy, into the deepest questions of existence. As 3i Atlas drifts onward, leaving behind only its light and the data we gathered, its riddles remain. Each one beckons, unsolved, into the dark. But mysteries are not the end of the story. They are the invitation to look again, to search harder, to wonder deeper. The comet does not answer, but it compels us to keep asking, to keep reaching, to keep turning our instruments toward the sky in hope of the next messenger that might whisper something new. The comet does not answer, but it compels us to keep asking. That, perhaps, is its most profound gift. A silent insistence that the questions are worth chasing even when the answers remain elusive. 3i Atlas is not just an object in the sky, it is a mirror reflecting our own hunger to know, our refusal to be satisfied with the horizon as it is. There is something extraordinary about living in this particular age, in this fleeting chapter of human history. For billions of years, comets like this must have passed unremarked, their beauty dissolving in the void with no eyes to see them. Dinosaurs never noticed. The first humans gathering under firelight never knew what streaked faintly across the heavens. But here we are, a species that has taught itself to build machines that can sweep the skies, instruments that can catch whispers of light, minds that can stitch together fragments into meaning. We are alive at the very moment when the galaxy's wandering debris becomes visible, catalogued, understood. What a privilege to exist just as the universe begins to open its secrets to us. When we look at 3i Atlas, we are not merely studying a comet. We are reaching across the gulf of stars to touch something that was forged elsewhere, matter that has traveled between suns. It is a physical connection to worlds we may never visit, to systems whose planets may have bloomed and died long before Earth was born. To know that such material now brushes past us is to feel part of a larger story, one in which our solar system is just a single chapter in a cosmic library. The poetry of it lies in the journey. Imagine the grains of dust escaping from the comet's surface, drifting free, each one a traveler in its own right. They may linger in interstellar space for eons, crossing voids where no starlight reaches, until at last gravity or chance carries them into another system. Perhaps one of those grains will land on a young planet's surface, sinking into soil or sea, mixing with native elements. In this way, the galaxy shares itself. Matter is not bound to one birthplace, it is woven into a web of exchange. To study 3i Atlas is to glimpse that cosmic commerce in action. We owe this revelation to the scientists and the instruments they have built, the telescopes sweeping the skies each night, the algorithms tirelessly comparing patterns, the teams coordinating across continents. Together they form a chorus of curiosity. Every spectrum, every image, every calculation is a note in the music of discovery. The comet would pass regardless, but without these tools and the people behind them, it would pass in silence. Gratitude is due not only to the cosmos for sending this messenger, but to ourselves for choosing to look up, to listen, to devote resources and ingenuity to understanding. What does it say about us that we care enough to track such fleeting wonders? Perhaps it says we know, at some deep level, that we are part of something vast. We are not separate from the galaxy, not spectators standing outside its arena. We are made of the same elements, shaped by the same physics, bound by the same gravity. To see a comet from another star is to be reminded that the boundary between out there and in here is only temporary. The universe is not distant, it is us. In that awareness lies a kind of solace. Our lives are brief, our civilizations fragile, our planet just one among countless others. Yet by turning our gaze outward, by noticing an interstellar traveler, we place ourselves in continuity with something much larger. We become participants in a story that stretches back to the dawn of time and will continue long after we are gone. The comet will leave, but the wonder it sparks remains, carried forward in memory, in science, in the ongoing dream of exploration. That is the true gift of 3i Atlas. Not only data for our models, but meaning for our imaginations. It whispers that curiosity is not a luxury, but a necessity, that wonder is as vital to us as oxygen. Without it, we shrink into ourselves. With it, we expand to meet the universe. Each interstellar visitor is a reminder that the cosmos has not run out of surprises, that there are still mysteries to chase, still reasons to look up. So as you sit here listening, perhaps in the quiet of your own night, remember that you are part of this moment. You share in the privilege of being alive when the galaxy's wanderers reveal themselves. You belong to the generation that has seen matter from other stars pass within reach. That is no small thing. It is the kind of wonder that anchors us, even as it calls us outward. If this story has stirred something in you, if you have felt the pull of the comet's long journey, the grandeur of its mystery, the thrill of our pursuit, I invite you to stay with us. Like the astronomers who share their data across the globe, our community grows stronger with every curious mind that joins. A simple gesture, a like, a subscription, keeps the circle unbroken, the conversation alive, the wonder shared. Your presence here matters, because this is what the sleepless how is for. To keep watch together, to marvel at the universe's strangeness and beauty. To remember that we are not alone in our longing to know. The night is vast, but in speaking of it, in watching together, it becomes a little less lonely. So let us carry this ancient wanderer with us, not just as a comet catalogued and measured, but as a symbol of what it means to be curious, fragile, and yet capable of wonder. Let us remember that even in the silence of space, the universe is always speaking, if only we have the patience to listen. Thank you for watching, for listening, for sharing your time under these same stars. Until the next mystery calls us back into the night, this has been the Sleepless How. Stay curious, stay awake to wonder, and above all, keep looking up.